Hello wonderful person, this is Anton, and today we're going to discuss the fascinating concept of megatsunamis, kind of like the ones we see in the movies, but in real life. And something that we've discussed just over a year ago, because there was a really massive megatsunami detected in Greenland. You can learn about this in one of the videos in the description. But why are we talking about this again? Well, because they happened again and more than once in the last couple of years. But I guess much more importantly because one of the biggest ones we've ever seen, a tsunami over 400 meters in height, only happened in August of 2025, so just a few months ago. But another one that happened a little bit earlier, the one in Canada, has now been finally analyzed and we now have a lot more to discuss here. Or, in other words, in just the last few years, there's actually been a relatively large increase in these megatsunamis, with 3 really large ones happening in the span of just a couple of years. And so let's discuss this concept a little bit more, but first let's actually talk about what megatsunamis are and what they're not. Because normally, when you hear the word tsunami, you may picture something that's produced by an earthquake and something that travels across the planet, potentially causing destruction to different locations. But these are usually caused by the movement of tectonic plates and do affect the entire ocean basin and not just the immediate location. But typically these ordinary tsunamis, even powerful ones, do not exceed heights of about 30 meters of 100 feet, except for some super rare locations on the planet. But we are actually discussing a different concept known as megatsunami, and despite the similarity in names, they're an entirely different phenomenon. This is not created by a tectonic shift, but usually by some kind of a substantial and sudden displacement of material, normally dirt, ground, rocks, or a large part of the mountain, that plunges directly into a body of water, displacing everything all at once. And though it could be also caused by some kind of a volcanic eruption, or maybe even some kind of a very large meteoroid striking the planet, in the majority of cases in the last few years, it was mostly the result of some kind of a landslide or rock slide. And here this direct displacement creates an immense splash, resulting in waves measuring hundreds of meters in height. And this right here is the famous record holder, the 1958 Lituya Bay megatsunami, signs of which are still visible even today. This was a wave of just over 500 meters in height, produced by a sudden landslide into the Lituya Bay. But in reality, the idea behind megatsunamis does not really have an official definition. We commonly use this to refer to very large waves that exceed 100 meters in height. But importantly, these waves are always localized. They're very powerful near the source, and they usually rise to their peak within just minutes, but they also dissipate pretty quickly as they travel farther away from the location. Although intriguingly, as we're going to discuss in a few minutes, there's another important phenomenon they create that was officially confirmed just a few months back. But it was once again this event in 1958 that cemented this concept of megatsunami and made it an official phenomenon. But it was always believed to be maybe kind of rare, something that might happen sometimes, but does not happen too often. Except that in just the last 5 years, we have seen a disturbing increase in number of these colossal waves, and luckily for us, so far, targeting remote glaciated regions in Alaska, Greenland, and Canada. And you can probably guess why they started to happen so suddenly. But we'll come back to this in a few minutes as well. Let's actually first discuss the most recent and the most shocking example that literally nobody expected. Something that happened not so far away from Juneau, Alaska. And it was actually in the location somewhere right here. Now the thing is, I'm looking at much older Google pictures, so they have not been updated yet, but I'm actually kind of curious to see what it's going to look like in a few months when they update the images. But we do have field photos. This is from the USGS website. And here we do have a before and after picture showing us what seems to have happened. And this right here was the source. This enormous chunk of mountain basically fell in the water, resulting in the destruction you see on the ground. And so on Sunday, August 10, 2025, an enormous landslide above the South Sawyer Glacier plunged into the fjord below, suddenly displacing an enormous amount of water. And this was actually detected by the seismic detectors nearby by the Alaska Earthquake Center, which saw a very unusual minor earthquake at 5:30 a.m. But the scale of this collapse was immense. This involved 100 million cubic meters of material, involving a huge amount of rock, collapsing and striking down the edge of the glacier, that then added 57 million cubic meters of ice, mixing and entering the water all at once, with the resulting displacement generating an enormous wave. Right now, based on the scientific analysis of the satellite data and the destruction we see on the ground, the maximum run-up height was approximately 470 to 500 meters or 1500 to 1600 feet. So just a little bit smaller than the Lituya Bay in 1958. And so this incredible measurement from the 2025 Tracy Arm Megatsunami is now the second tallest megatsunami ever detected in history. And it just happened a few months back. And here the destructive force becomes pretty apparent if you just look at the photos. All of the vegetation below a certain height was completely eliminated, and even underlying rock and soil were displaced as well. In certain locations, huge house-sized chunks of rock were displaced by hundreds of meters. But surprisingly, even after traveling for about 5.6 kilometers and approaching this island, the wave was still pretty high, because even the vegetation on this island did not survive. So it was at least 30 meters in height even here. But luckily for us, there was no one around to witness it, and so nobody died. No injuries, no fatalities, no damage. Actually, maybe a little bit of damage. Some of the kayaking equipment on the harbor island was reportedly swept away. But just like the previous megatsunami in 2023 in Greenland, this one here also generated something we didn't actually know existed until now. Here, a completely new physical phenomenon seems to form inside these fjords because of their very narrow geography. They seem to produce what's known as a sage, essentially a kind of a sloshing phenomenon that you usually see in a bathtub or in any small body of water like in a swimming pool, where a wave basically travels between two sides and continuously sloshes around. And while we know that the 2023 megatsunami generated a sage that lasted for at least 1 week. But surprisingly, even here, the water seemed to slosh back and forth across a large segment of the fjord for at least 34 hours. And this was also surprisingly visible to the seismic detectors because there was this really bizarre shaking the sage was producing. Although I guess what's not clear right now is why exactly did the sage here only last for 34 hours, but the one in Greenland lasted for 9 days. Either way, these bizarre phenomena seem to be unique to megatsunamis and definitely result in additional damage to everything nearby, because in this case the waves they produce are very likely enormous in size. But, as I mentioned, the Tracy Arm event is not an isolated incident. It seems to be a part of a pattern visible across different Arctic regions that started happening more and more. And that's because except for the Dixon Fjord or the Greenland megatsunami in 2023, and apart from this one in Alaska, we actually have another one in December of 2024 on the Tahini River in Yukon. So essentially very close to where this is, but in Canada. But in this case, this was caused by something a little bit different. Here, a very steep slope seems to have failed above the Tahini River, resulting in a landslide of approximately 118,000 cubic meters of ice-dirt mixture. But because the river itself was already frozen, this basically created a very bizarre ice-studded tsunami, or essentially tsunami covered entirely in huge chunks of ice. And the wave here was so powerful that it was easily able to rip up trees and moved huge chunks of ice for hundreds of meters. It was even able to displace ice that was frozen solid on the bottom of the river, implying an enormously powerful wave. All of this was recently reported in the study you can find in the description. And the thing is, over the last 10 years, there's actually been a kind of a pattern of these events happening in very similar locations but with higher frequency. We had the 2015 Tayan Fjord landslide and tsunami in Alaska, the 2017 landslide and tsunami in Karet Fjord in Greenland, the 2020 landslide in BC in Canada, and a few less known and smaller ones in 2007 and 2000. With pretty much all of these events being the result of some kind of a major landslide. But I guess why? What's actually driving these megatsunamis, and why so many recently? Well, first of all, the increase in documented megatsunamis, particularly those because of landslides, is first of all the result of better detection technologies. But the thing is, many of them were detected using seismic sensors that have existed for at least 30 years. And so the other explanation here is, of course, dramatic environmental changes in various locations in the Arctic. And here the core scientific explanation involves two parts. First, we have what's known as glacial debuttressing. For thousands of years, massive glaciers acted as a kind of a support or buttress, literally holding up a lot of these very steep and very fragile fjords and various river valleys. In other words, they kind of created a natural scaffolding. But as global temperatures rise and as these glaciers retreat and thin, most of this ice support starts melting and disappearing, with many steep slopes that are already stressed by glacial erosion suddenly becoming very vulnerable to catastrophic failure. And this is exactly what happened in both 2023 Greenland tsunami and the more recent Tracy Arm tsunami in Alaska. Both of them were extremely close to retreating glaciers that were slowly melting for the past 2 decades. But the second problem here is also the permafrost thaw. In a lot of Arctic regions such as in Greenland, Alaska, and in Canada, frozen ground or permafrost usually stabilizes mountainous regions. It essentially solidifies ground and prevents it from moving too much. But once again, because of the warming Arctic and because of the permafrost thawing, the strength of various mountainous regions started to decrease and the slope instability started to increase dramatically. And so when you combine retreating glaciers and thawing permafrost together, it creates a perfect environment for landslides that then suddenly displace enormous amounts of water. And though luckily for us so far, none of this was too damaging or produced any immediate effects, it's actually only a matter of time before this happens somewhere much closer to some kind of a settlement, and before this results in fatalities. And so a lot of recent scientific studies try to focus on using technology to detect and address these growing hazards, with one major discovery being precursor signals. And so here, investigations into the 2017 Carrot Fjord disaster, which actually did produce a megatsunami that damaged one of the settlements, found evidence for seismic signals that preceded massive landslides, suggesting that before the landslide occurs, there seems to be some kind of a shaking that's identifiable, resulting from some kind of a gradual movement a few hours before the event. And that means that there might be a way to detect this before it happens near a much larger settlement and before a larger catastrophe. Additionally, by using satellite radar imaging and by using seismic energy analysis, it's now possible to analyze a lot of slopes that could be unstable and thus anticipate a potential landslide before it happens. Which in this case would be very important because, unlike a typical tsunami that takes hours to arrive, in many cases these waves arrive almost instantly and do not produce a lot of warnings. And this is especially important for my home country of Canada. One such event in 2020 in the Elliott Creek in British Columbia produced such a powerful event that the wave was able to travel for over 60 kilometers, devastating pretty much everything in its wake. Luckily, once again, there were no settlements, but there could have been. As a matter of fact, quite a few settlements exist along other rivers that do have very similar problems. And so the overall scientific consensus here is pretty clear. Landslides are becoming a bit of a concern for certain regions, especially regions with glaciers and a lot of permafrost. And certain regions in the Arctic may need to prepare for a potential disaster. But the obvious goal here is not to kind of scare anyone and not to hype this, but to really observe the facts. Because of the changes on our planet and because of the sudden increase in these megatsunamis, we need to start to understand what additional hazards we have to deal with and do so actively by improving our monitoring systems and by preparing for these potential disasters, and especially in those regions where this could physically happen. Which means that this is definitely something that needs to be studied more and something that we cannot just ignore. But at least for now, that's kind of, I guess, all we know. We'll definitely discuss this more because megatsunamis are just kind of fascinating for a lot of different reasons, and because one of the biggest ones ever, just happened a few months back, and I'm sure not a lot of people know about this. Hello wonderful person, this is Anton, and today we're going to discuss the idea referred to as Milankovitch cycles, a phenomenon that scientists believe is responsible for cyclical climatic changes on planet Earth, and that for the past few million years influenced the formation of things like, for example, glaciers and the periods we sometimes refer to as the Ice Age periods, as well as resulted in additional changes such as increased or decreased precipitation and the expansion of deserts like the Sahara. And this is of course something we've known for a long time. For millions of years, Earth's climate has shifted between long frigid ice ages and much milder, shorter and warmer periods referred to as interglacials. And today we actually think all of this is governed entirely by other planetary bodies, or essentially by subtle nudges here and there and periodic shifts in our planetary movement when it comes to its orbit around the Sun. And so it's these orbital variations that we refer to as Milankovitch cycles, named after Milutin Milankovitch, who provided a definitive proof for this back in the 1920s. And today we know that these cycles definitely play a huge role in the climate on the planet, and especially in something referred to as climatic forcing. They change the distribution of solar radiation on the planet, which can then dramatically affect certain areas in just a few hundred years. But for decades, many studies in regards to this were focused on, obviously, the Sun and larger planets like Jupiter and Saturn. As in, most of this is very likely caused by Jupiter, but obviously not everything. And it was really some of the recent and more detailed studies that started to uncover that there's also something else going on here. And specifically, as you can probably tell from the title of this video, much smaller planets like Venus and even Mars seem to play a pretty big role as well. And so in this video we're going to explore some of these new discoveries and what we actually know about this, and specifically focus on this recent study on the effects from these gravitational nudges from our neighbor Mars. But just in case you have no idea what these cycles are and how all of this works, let's do a very brief overview. So how exactly does this work? Well, this NASA link in the description explains this in a lot of detail, but in essence there are really only three components. First we have the eccentricity of the planet. This is the shape of Earth's orbit around the Sun. Is it more circular or is it more elliptical? And so when the orbit is more elliptical or elongated, the variation in distance between Earth and the Sun increases a little bit more. And this affects how much solar radiation Earth gets throughout the year. Today, scientists are pretty certain that this is definitely caused by Jupiter and Saturn. And it seems to manifest itself in a very stable cycle that's about 405,000 years long. And here it actually has three separate periods. And so this much longer stable cycle contains much shorter cycles of around 95,000 and 124,000 years, which loosely combine to create the 100,000 year cycle that we actually observe in a lot of geological data. Then we have something referred to as obliquity. This is essentially the Earth's rotational axis. Now currently the axis sits at about 23.4 degrees, but as you can see here it varies between 22.1 and 24.5. And this takes approximately 41,000 years. And so here a greater tilt results in more extreme seasonal temperature variations and thus more extreme weather, whereas the decreased tilt promotes milder seasons, but also encourages a cooling trend, which actually can create a glacial period during this time. And that's mostly because there is less sunlight in the summer, and so at very high latitudes, it becomes very difficult to melt previous ice and to warm up the ground. And then we have the wobble or the axial precession. This essentially makes Earth kind of similar to a spinning top. And this cycle is about 25,700 years long and generally affects which of the hemispheres ends up getting more sun, especially when Earth is super close to the Sun. And so this drives seasonal extremes, and combined with other cycles, can also create an additional primary cycle of 21,000 years. And so altogether, these cycles define Earth's solar forcing, shaping glacial and interglacial periods that have dominated Earth's history for the past 2 to 3 million years. But apart from changing the amount of sunlight, these cycles also do something else. For example, one major historical puzzle here is sometimes referred to as the 100,000 year problem. And specifically here, although the 100,000 year cycle seems to dominate variations in ice volumes on the planet, at least over the past 800,000 years, generally, orbital eccentricity contributes much less to changes in solar radiation compared to other cycles. And so there's actually a bit of a discrepancy in how much sunlight Earth is getting and by how much ice seems to decrease and increase every 100,000 years. And so here this discrepancy suggests that Earth's climate system contains a lot of internal feedback mechanisms, most likely associated with levels of CO2 and potentially other greenhouse gases that essentially get released or get trapped inside during certain events caused by these cycles. For example, even just a little bit more sunlight may actually start thawing a lot of permafrost, which can then start releasing a lot of methane and dramatically decrease the levels of ice in a relatively short time. Furthermore, additional studies from the last few years highlight that a lot of these climatic changes don't just affect the levels of ice or affect the rain, for example. They seem to be also linked to Earth's internal processes such as volcanism. This was actually reported in one of the recent studies you can find in the description, but turns out that variations in global climate, and specifically advances and retreats of massive ice sheets, which also result in very different sea level changes, seem to physically modulate volcanic activity on relatively long timescales of thousands to tens of thousands of years. Or just to rephrase this, volcanism seems to be also directly affected by a lot of these cycles, and specifically by the movement of glaciers. So for example, the retreat of glaciers or glacial unloading reduces the pressure on Earth's crust, which can lead to decompression melting in the underlying mantle. And this actually dramatically increases the rate of volcanoes, and thus increases the amount of stuff being released by volcanoes long term. And so by having less glaciers, we actually get more volcanism, which then starts to cool down the climate long term because of all of the gases released from the volcanic eruptions. And this is not just a hypothesis, there's actual evidence. Milankovitch cycles of 23, 41, and 100,000 years seem to appear directly correlated to global volcanic activity, suggesting a direct connection. So essentially, these cycles seem to play a much bigger role on planet Earth than we ever expected. But once again, the foundation for these cycles is of course the result of gravitational interactions with a lot of solar system bodies. But scientists never really thought it's going to be smaller bodies like Mars and Venus. And so now we have this new study that reveals that Mars seems to exert a particularly strong and often surprising influence on the planet that was previously ignored. And so here, by using computer simulations and models, and by essentially varying the mass of Mars compared to other planets, and then tracking the resulting changes in the Earth's orbital evolution, scientists were able to discover exactly what Mars's role seems to be. And so first of all, here the simulation officially confirmed that the most stable cycle is approximately 105,000 years. This is once again mostly driven by the larger planets. As a matter of fact, the cycle persists independent of other planets, just because Jupiter is the most massive planet in the solar system. But surprisingly, almost every other cycle seems to change dramatically if you actually change the mass of Mars. And so here, by changing the mass of Mars from 0 all the way to 1000%, scientists discovered that the orbital changes on planet Earth seem to actually be quite extreme. For example, when it comes to the cycles responsible for the ice ages, the 100,000 eccentricity cycles seem to actually heavily rely on Mars's gravitational presence. And so in the simulations, as Mars became more massive, a lot of these 100,000-year cycles lengthened and gained power. Alternatively, when Mars's mass was 0, these cycles weakened and became almost insignificant. And so this potentially suggests that one of the main reasons we might even have ice ages is because of Mars. But here this was not even the most surprising discovery. The most striking discovery was of a much longer cycle, 2.4 million years. This is a very long-term climate fluctuation and is a kind of a grand cycle when it comes to eccentricity, and it seems to be tied to the slow rotation rates of Earth's and Mars's orbits and disappears entirely when Mars is 0 mass. We've actually briefly discussed this in one of the previous videos in the description, but basically here, Mars seems to create an actual new cycle on the planet that we've never really known about before until some of the more recent studies. And so this grand cycle of 2.4 million years only exists because of Mars, and only because it seems to create the right gravitational resonance with our own planet. And obviously our planet seems to influence Mars as well, so it also has its own climate changes because of Earth. And then the last cycle, the obliquity cycle, seems to be also sensitive to the Mars's mass. Here the familiar 41,000-year cycle seems to lengthen as Mars becomes more massive, with simulations showing that if Mars was 10 times as massive, the 41,000-year cycle would shift, becoming the dominant cycle and dramatically changing the climatic changes on the planet roughly around every 45,000 years. This would actually dramatically alter the patterns of ice sheets and possibly even cause Earth to become an ice planet. And so in many of these experiments, scientists demonstrated that the mass of Mars seems to be the main controlling factor in driving a lot of Earth's climatic shifts because of these Milankovitch cycles, with these findings showing us that Earth's Milankovitch cycles are not just a product of our planetary dance with the Sun and Jupiter, but is definitely a result of a lot of planetary interactions with pretty much most of our neighbors. And this is of course important for at least two main reasons. First, understanding these predictable climatic changes helps us establish highly accurate baselines for what we naturally expect to happen on the planet over the next few thousands of years. For example, studies using this knowledge predicted that the next ice age should occur in about 10,000 years from now. But by establishing these natural baselines, we can now start quantifying when it's actually going to happen because of obviously human emissions and a lot of additional climatic changes in the last couple of centuries. So for example, we know that additional emissions of carbon dioxide and huge amounts of methane, both natural and artificial, seem to have already diverted some of this climatic shift from its natural course. But at the moment it's unclear if human-made climate change is going to completely prevent the next ice age from happening, or if it's just going to create some kind of a freak weather every year, as a lot of additional mechanisms on the planet try to basically rebalance themselves and force the climatic changes to continue into the ice age despite all of these greenhouse gases. So basically right now nobody actually knows what's going to happen, but this is why these studies are kind of important. And then at the same time, a lot of these results also obviously tell us a little bit more about exoplanetary habitability. Because by studying these Milankovitch cycles, we learn about interplanetary interaction and various planetary changes, and learn to understand how a lot of these Mars-type perturbers may shift certain cycles, producing slightly different exoplanetary architectures. And so, for example, if we do discover some kind of an exciting planet out there, for example maybe in the TRAPPIST-1 system, we have to then start understanding how the additional 6 planets in the system influence that one planet that we now want to understand. And for TRAPPIST-1 system, where all of the planets are pretty close to each other, the Milankovitch cycles there would be pretty extreme. And so the main point here would be finding planetary configurations where we can, in theory, have a very stable climate long term, without any major shifts. And so for example, when we look at Mars, we know that Mars is definitely not the right planet. And that's because over time Mars tilts its axis by something like 60 degrees. Which essentially means that this particular planet would just not have stable conditions long term and would unlikely to have habitable conditions for a very long time. And so here we're looking for a terrestrial planet orbiting a distant star, but that seems to have very similar orbital configurations and only experiences very mild climate variations that prevent dramatic freezing or dramatic runaway of various gases. And basically it does have seasons, but nothing extreme, because based on Earth, we think that this is what's conducive for complex life. But ultimately, based on this new study, we now have pretty strong evidence that even the humble Mars, which is very often overlooked when it comes to orbital shifts, seems to play a surprisingly important role in shaping the seasonal rhythms on our planet. And so here we're talking about the ice ages and the long-term stability of the entire planet. And that by itself is of course just a little bit surprising. Hello wonderful person, this is Anton, and today we're going to discuss some of the recent updates about the most catastrophic event that happened to planet Earth, the idea known as the Giant Impact Hypothesis. The event that represented one of the most destructive collisions in the history of the solar system that eventually led to the formation of modern Earth and of course our Moon. And for decades the primary question surrounding this event was mostly focusing on the lunar formation and on various unusual similarities between Earth and the Moon. And although some studies that we discussed previously that you can also find in the description potentially questioned this event, basically suggesting that maybe it was something entirely different, at the moment most scientists seem to agree that something catastrophic indeed happened 4.4 billion years ago, because otherwise it's very difficult to explain the formation of the Moon. But today we're going to discuss this somewhat recent research that suggests the collision between the hypothetical planet Theia and early Earth might have been far more significant than just giving us the Moon. It might have been responsible for basically forming early life. And so let's discuss this idea and this study in a bit more detail, but here I guess let's start with the very brief history of early Earth. And here we have to rewind time by approximately 4.5 billion years. The early solar system was a very chaotic place. Planets were still forming, a lot of things were still colliding, and quite a few planets, including potentially some of the biggest planets, Jupiter, Saturn, Uranus and Neptune, all seem to have experienced major collisions. And some of these early planets potentially shared very similar orbits, possibly even getting stuck in somewhat prominent positions such as Lagrange points, which do allow certain objects to share the same orbital parameters. And so the hypothesis here was that at least one of these objects was maybe somewhat similar in size to Mars, but it was also sharing an orbit with planet Earth. But because there was so much interaction in the solar system, at some point this object got dislodged. And this object, referred to as Theia, eventually collided with early Earth, with the immense energy from the impact ejecting a vast amount of debris into the orbit around the planet, which eventually coalesced to form the Moon. And so this particular formation hypothesis has been studied for many decades and right now does seem to make a lot of sense. But this collision might have actually had a much more profound consequence for our planet. Because according to quite a few cosmochemical studies, or essentially studies on the chemistry of various planetary objects, Earth as we know it today seems to have accreted approximately 5 to 10% of its entire mass from something known as carbonaceous materials, also known as CCs, which usually refers to any substance rich in carbon, such as for example organic compounds like graphite, or a lot of stuff we find inside asteroids and meteorites. And these meteorites are usually referred to as carbonaceous chondrites. Any meteorite containing a lot of these chunks and a lot of these volatile chemicals, mostly composed of hydrogen and carbon, that can then easily vaporize, but most importantly, is basically essential for life. But there's a bit of a problem. Based on what we know about the planet, Earth seems to have formed much closer to the Sun. And temperatures near the Sun, even back in the days, were much too high for these volatile materials to condense and become part of these early rocky planets. Or just to rephrase this, we don't really expect so many volatiles and so many carbonaceous materials to be present around planet Earth. And that means that early Earth might have been quite dry and quite barren, not so different from planets like, for example, Mercury. So it would most likely be some kind of a wasteland, completely incapable of supporting life. And that's where this Theia hypothesis steps in, because it might have been a massive delivery truck. This new study, published in Science Advances by Pascal Courtache and his partner Klaus Mesger, strongly suggests that Theia originated much farther in the solar system, in a location where a lot of volatiles very likely existed. And when this volatile-rich Theia collided with proto-Earth, it didn't just create the moon, it also delivered a lot of these essential ingredients directly to our planet. And in this case, researchers used a very specific chemical model, mostly focusing on different isotopes, for example manganese and chromium. And this allowed them to precisely track the first few millions of years of Earth's formation and understand the chemical makeup of a lot of the building blocks, with findings indicating that early Earth, and very likely a lot of other rocky planets like Mars, Mercury, and Venus, dramatically changed their composition in the first 3 million years, mostly because of a lot of dust and gas being delivered to their surface. But following this initial period, the process of getting new matter mostly stopped, with the result being, well, what we see right now around other planets. Planets closer to the Sun, so Mercury and Venus, were depleted in volatile elements, whereas planets like Mars potentially had some elements, but eventually lost them due to the lack of mass. But Earth does contain a lot of volatiles, so they must have come from something else. In this case, Theia seems to make the most sense. And here this object was very likely some kind of a small stony planet, but enriched in carbon and organic compounds, with all these compounds suddenly delivered to the Earth's surface. But interestingly, this is just one of 2 studies released very recently that kind of implies something very similar. There's actually another study you see right here by Branco, Mercado, and Raymond that suggests Theia didn't just bring volatiles, it also very likely delivered a lot of water. And this is a puzzle for geologists because water is generally much less dense, meaning that in theory it should rise to the crust or the oceans. But here the simulations from the study suggest that Theia delivered all of this water, mostly into the Earth's mantle, and there hasn't been enough time for most of it to reach the surface yet. And so deep inside our planet there is very likely a lot of leftover water, representing a direct legacy of this enormous impact, with both studies providing validation for cosmochemical studies, explaining how Earth acquired significant fraction of carbonaceous material and a huge amount of water on top of this, with these 2 propositions explaining and solving quite a lot of unusual mysteries. For example, previous chemical studies on Earth and Mars show that in case of our planet, it seems to have 10 to 15% carbonaceous material, while our red neighbor, Mars, seems to just have a few percent or just a fraction of the material. And that doesn't really make sense because Mars is much farther from the Sun, so technically it should contain more. And so if carbonaceous material in the inner solar system was mainly in the form of these large planetary embryos, that would then collide with various objects, it would be much easier to explain why some planets seem to have this misbalance. Here, Earth would receive a huge dose, while Mars potentially only experienced much smaller collisions, and thus much less delivery of various volatiles. And so here, this particular model actually questions the origin of Theia. it was unlikely to have come from the same orbital parameter as Earth, and was extremely more likely to be some kind of a volatile rich body coming from the outer solar system, possibly even beyond the asteroid belt and beyond Jupiter. And here the simulations also suggest that it was really Jupiter and Saturn that mostly scattered a lot of these materials early on, very likely causing most of these collisions. But I guess the main question here is, so why is this important and why does this matter? Well, in this case, the implications are quite vast and do extend way beyond our planet. Because obviously in this case, Earth is also the only planet where life has been officially confirmed and also directly depends on these two things Theia brought to Earth: organic molecules and carbonaceous materials and a lot of water. And so one of the potential implications here is, of course, in regards to the origins of life. Maybe life requires these dramatic events, and actually very specific events, very likely involving giant volatile-rich impactors from the outer star system, to suddenly receive a lot of essential building blocks for life, and potentially a lot of other stuff, in order to kickstart early formation of life on the planet. Which also potentially suggests that life in the universe is maybe not so common after all. And so even though today most researchers focus on Earth-like worlds when trying to discover some kind of a habitable planet out there, the conclusions from these two studies suggest that we're still just going to find some kind of a barren rock unlikely to support any life at all. And it's really only certain rocks that experience these Theia-like impacts that then maybe have a chance for life to finally form. But even in this case would still require quite a specific balance and quite a few critical things to happen at the right time. And so far these two studies put a strong emphasis on these moon-forming impacts as not just being geological events, but also being biologically foundational, at least for the history of our own planet. And although there were some limitations in the study, such as not accounting for all of the complex dynamics in the early gas disk, the research still provides powerful dynamical validation for most chemical studies involving planets and offers us a plausible scenario for how Earth became a unique life-supporting planet. Which in summary means that the story of Theia is no longer just about the moon, it's now about the life itself. This event potentially led to the emergence of life that then physically transformed the planet into the Earth we see today, making this a stark reminder that sometimes our existence might just be the result of very precise and even somewhat lucky events that may not be very common out there. But once again, this is, at least for now, still a hypothesis. And if you disagree, let me know why in the comments below. But we'll definitely come back and discuss this more in some of the future videos, because this is probably one of the most fascinating topics when it comes to the formation of Earth and the Moon. Hello wonderful person, this is Anton, and today we're going to discuss one of the potential resolutions for a somewhat unusual biological mystery that puzzled scientists for hundreds of years. The puzzle in regards to the origins of life. Although to be more specific, the puzzle in regards to the origins of life on the surface of the planet as opposed to in the ocean. With the question being, why is it that it actually took billions of years for life to establish itself on the surface while it actually existed for almost 4 billion years in the oceans? And why is it that it took so long for life to diversify and become super complex, only establishing itself on land in the last 450 million years, which is really only like 10% of the lifetime of planet Earth? And that's despite the fact that relatively complex cells, such as for example cyanobacteria cells, existed for almost 3 billion years in the oceans. Yet based on all of the fossil evidence, we know that there was nothing going on land prior to the era known as the Cambrian. And in the last few decades, there's obviously been quite a few attempts to try to explain this, and quite a few explanations. With the one explanation that seems to be mostly accepted now, not really being very satisfactory. Mostly because it actually just states that this is some kind of an intrinsic property of life, and it just takes a really long time for complex life to develop and to conquer the surface of the planet. In this case, for planet Earth, it took almost 4 billion years. But the thing is, there's really no evidence for this assumption, or I guess no evidence that life requires any time to evolve, because the evidence we have suggests that evolution seems to happen in leaps and jumps, such as for example during Cambrian. The life actually evolved super quickly, diversified very quickly as well, and managed to go from relatively simple life to very complex life in just a few million years. In the process also beginning the conquest of land. And so something in this explanation basically just doesn't add up, which is essentially the reason for this new study by Jin-Jun Liu and his team. And here the focus is on trying to explain this using actual physical evidence and the idea behind iodine. Specifically, iodine cycle, that's actually one of the cycles on the planet we don't really know as much about. But there is something we've discovered about iodine in the last few years that potentially serves as an answer to many of these mysteries. Iodine is surprisingly similar to the famous, or I guess infamous, CFCs when it comes to ozone depletion. And so in the last few years, we've had quite a few studies analyzing and discovering the effects of iodine on the destruction of ozone layer. And it actually seems to come from a lot of different locations, many of which are entirely natural and are extremely difficult to control. But today we know that it seems to have quite a dramatic effect on the ozone and substantially increases the hole size pretty much every year. And in this case, the destruction of ozone seems to be very similar to how it's usually done by the CFCs, the chlorofluorocarbons. Here, as a result of photolysis or the destruction of the molecules by solar radiation, various reactive molecules are released into the upper atmosphere, and in this case into the stratosphere, which then serves as a catalyst in destroying ozone in a relatively short time. Now in the CFC molecule, the atom responsible for everything is chlorine, but turns out that iodine pretty much does the same thing. And so quite a lot of iodine-driven cycles seem to be also responsible for the ozone depletion, and surprisingly, in some cases, can even destroy ozone faster than chlorine. But intriguingly, the overall emission of iodine today is not really that dramatic. As a matter of fact, it seems to be absorbed by a lot of stuff in the oceans and also by the soil itself, and so the contribution to the ozone depletion, at least for now, is manageable and not really a concern. But the researchers behind the study realized that it might have been not always the case if we go back in time. Because it looks like billions of years ago, the absorption levels of iodine were much lower, suggesting much higher levels of iodine in the atmosphere. And so in a nutshell, the main explanation in this study involves iodine cycle. And so in essence, the explanation for why life on Earth took so long to actually establish itself on the surface involves this iodine cycle that might have been very different for billions of years. And so in this case, by conducting a relatively thorough geological analysis, and by focusing on different lines of evidence and different sources, the team was able to reconstruct a kind of an iodine dynamic for early Earth, showing that back in the days, for billions of years, the atmospheric iodine was really high, and the absorption of iodine in the oceans and on Earth was relatively low. And that basically suggested one thing. Even though there was a lot of oxygen in the atmosphere, there was also quite a lot of inorganic iodine mixing and interacting with everything. And the much higher levels of marine iodine, which actually results in the production of an iodine salt, allowed it to travel in the upper atmosphere, reaching the stratosphere, and basically interacting with any attempts to create ozone. Here the evidence suggests that this unusual salt was quite prevalent in the early history, and the emissions of this inorganic iodine extremely likely disrupted ozone formation, with the additional simulations and photochemical calculations suggesting that even a relatively small increase in these inorganic marine iodides would very likely result in a complete depletion of ozone much faster than it would happen through the production of CFCs. And so the conclusion here is that for approximately 2.5 billion years, it was almost like some kind of a battle between oxygen and iodine, with the iodine constantly winning and preventing the formation of an ozone layer, even though there was quite a lot of oxygen. And that's even despite the fact that during some periods there was actually quite a lot of oxygen, and the atmosphere should have been enriched in ozone very quickly. But the iodine would constantly destroy it, which would cover the surface of the planet in relatively powerful UV radiation that gave life on Earth no chance to survive. And technically, by being a catalyst, iodine should have been really successful at destroying all of the ozone, even to this day. Yet something happened, and that's I guess the mystery. Approximately 500 million years ago, for some reason, the atmospheric ozone suddenly stabilized, and during the Phanerozoic period, that's when life suddenly started to become more complex and eventually started to conquer land. Now it's obviously not clear exactly why this happened and what exactly happened, but I guess here we can make some speculations. We know that iodine is also one of the heaviest elements that's technically required by a lot of living systems. As a matter of fact, after tungsten, it's the second heaviest element required for life. But for a lot of primitive life, it could technically be replaced by something else. Yet for complex life, like for example for any vertebrates, it is absolutely critical in the functioning of a lot of systems, specifically endocrine system, the messenger system involving hormones that very likely evolved approximately 450 million years ago. And according to modern biological studies, some of the early thyroid hormones, the ones involving iodine, seem to have evolved in these little guys known as urbilaterians, with all of the animals that evolved from them basically requiring iodine for something. Likewise, many other organisms, such as various types of algae, including the famous kelp, developed an ability to store a lot of iodide, and in many cases for unknown reasons. Intriguingly, kelp also evolved around the same time, approximately 450 million years ago. And so one potential resolution here is that as the life started to evolve in the oceans, and as it absorbed some of the iodine that would have formed some of the salts and escaped into the atmosphere, it essentially allowed oxygen to proliferate and to suddenly become dominant in the upper atmosphere. And this might have resulted in the production of ozone, which eventually created conditions where life could now establish itself on the surface. And so in some sense, maybe it was actually life that helped itself after all. By evolving the ability to absorb and require a lot of iodine, it dropped the amount of iodine in the atmosphere just enough to allow the development of ozone. But this is of course just one of the potential explanations and just an assumption, and right now there's really no evidence for this either. Because the only evidence we seem to have is geological and does actually suggest that iodine levels, at least in the atmosphere, decreased approximately 500 million years ago. And the thing is, if this study is correct, it finally settles one of the major mysteries. The mystery for why life could not establish itself on the surface for such a long time, and more importantly confirming that it's really not the length in this case that's important, or basically even though it was billions of years, it could have technically happened much earlier, but the actual answer seems to be chemical after all, and specifically in regards to ozone. It seems to be the ozone layer that prevented the formation of more complex surface life, and once ozone became permanent and established, it started to protect the planet for millions and millions of years, transforming the planet as we know it today. And so in this case, this origin and diversification of complex life may really be the result of an unusual chemical battle that was going on for billions of years and was finally won by oxygen and eventually ozone roughly around 500 million years ago. Naturally, this is just the first such study though, so it will probably take time to establish if this is correct or not, and more importantly to answer the question of, okay, so what exactly decreased the iodine, and why did the ozone form 500 million years ago and not before that? Okay, today we're going to discuss another super exciting study, this time in regards to the origin of terrestrial life on planet Earth. Or basically the idea of the history of life only on land. So how exactly did terrestrial life begin? And what were some of the first complex organisms that at some point came out of the water and started to settle on land? And normally when biologists discuss this, they usually focus on the big players. So in this case, things like plants, or as we've discussed somewhat recently, potentially types of organisms that used to be everywhere but no longer exist. Here I'm referring to very strange prototaxites. And this is something we've discussed recently and something you can learn about in the video in the description. But basically here the story was that approximately 470 million years ago, or possibly 500 million years ago, some of the first plants decided to colonize land and slowly settled on the surface. And so here for a very long time, biologists imagined this period as a kind of a somewhat bare, but also somewhat green landscape that contained a lot of first, but also somewhat tiny, green plants. Which was then followed by some of the first animals, very likely fish and certain types of arthropods, that started to spread from the seashore to land and eventually evolved the ability to walk. But that's the story we usually read in various textbooks, and that's what scientists assumed before. But the thing is, based on some of the recent evidence, including this major study you can find in the description below, a study from the Okinawa Institute of Science and Technology, that now basically suggests a lot of these previous assumptions seem to be missing a crucial chapter that might have been much longer than we ever imagined. And specifically here, for hundreds of millions of years before the first plant, or even before the formation of the first leaf, the land was already possibly transformed by a hidden kingdom that was genetically much closer to us, animals, than to plants. And here we're talking about fungi, or basically mushrooms. And so in this video we're going to briefly discuss how the fungi were probably some of the first engineers on the surface of the planet, and how they were most likely the original ecosystem that established everything else for plants and animals that arrived afterwards. And so here we're going to discuss some of these new discoveries that seem to push the history of fungi by approximately 1 billion years, and basically discuss how without them, complex life on land might have never even happened at all. But first, let's discuss the obvious. Why is this the first time we actually hear about this? Or at least I guess I hear about this. Well, in this case, this is really in regards to fossils and, of course, archaeology. One of the main reasons we've underestimated fungi is because they're absolutely horrible at living fossils. So, unlike animals that usually contain a lot of bones, or plants that usually contain woody stems, a typical fungus is made out of soft, fleshy tissues that degrade extremely quickly. As a matter of fact, they actually degrade so quickly that it was only recently we've discovered that humans that lived thousands of years ago potentially used a lot more fungi than we imagined. And that was discovered by accident because certain teeth contained DNA that could have only come from fungus, implying that it was very likely consumed. Now, that's obviously not what we're talking about today, but the point is that fungi do not leave a lot of fossils. They do sometimes, but just extremely rarely. And that's of course because most fungal structures contain these thread-like hypha, which are normally microscopic in size, and first of all fall apart pretty quickly, but second of all can be confused with other microbes. So it's pretty easy to misidentify them. And because they don't generally produce any hard minerals, or contain any hard parts, they only enter the fossil record under very specific conditions. And for many decades in archaeology, when it comes to fungal history, there was always this gold standard. You can actually see a sample of this in this image. This is what's known as the Rhynie chert, an ancient rock that's approximately 400 million years old that was discovered in Scotland, and that surprisingly was able to somehow preserve a lot of these early fungi very, very well. Although in this case, it's actually fungi interacting with some of these earliest plants, which is possibly one of the main reasons why the fungi were able to fossilize as well. And so when it comes to fungi fossils, this is the only definitive fossil we have that suggests fungi existed on Earth 400 million years ago. But a lot of biologists believe there had to be more and possibly even older samples. And mostly because of a lot of different types of DNA analysis. Or basically when you try to compare DNA of various fungi, it does suggest that fungi diverged from a common fungi ancestor much earlier. In this case, at least 1.2 to maybe 1.5 billion years ago. We'll come back to this particular concept in a few seconds. But here we even had some really unusual and somewhat controversial fossils, or technically somewhat controversial cryptic clues, from South Africa. Here, in a location referred to as the Ongiluk Formation, researchers discovered 2.4 billion year old basaltic rock that seemed to contain something resembling a fungal fossil as well. And if these are indeed fungi, it would mean they existed much before the atmosphere even had oxygen, and possibly in conditions on the planet that were extremely different from anything today. But after this discovery in 2017, there hasn't really been additional confirmation, and so we don't really know how accurate this is. Or in other words, at the moment biologists are not entirely certain what exactly this fossil is. So for all we know, it could actually be some kind of a different organism resembling a bacteria. But in 2019, there was a massive breakthrough. A breakthrough in regards to the timeline when it comes to mushrooms. And this time all of this came from the Canadian Arctic. And here this was a very unusual fossilized fungus referred to as Orasaphira giralde. And this one was preserved in a rock that was at least 1 billion years old. And so here we had a definitive proof that fungi seem to be present on land for at least twice as long as previously thought, and for at least twice as long as plants. And this was actually a game changer because it showed that fungi were likely already living on land, or at least in a shallow water, which is not something we knew before. But here the question was, okay, so can we actually fill the other gaps in the fossils? And can we find out how accurate this is? And when exactly fungi potentially started on land? And of course, what they were doing there. Well, this is where we have this new study from just a few weeks back. Now, once again, because mushrooms don't biomineralize very well, or basically, since they don't leave a lot of fossils, researchers have to rely on a molecular clock, which usually measures DNA mutations, to estimate when certain species diverged. This is, for example, how we know when humans appeared, and when humans diverged from cousins like the Neanderthals and Denisovans. And so basically here, by looking at DNA mutations, it's possible to estimate an overall timeline. And so here the team from Okinawa used a brilliant new method involving horizontal gene transfer, or basically when genes jump from one species to the other, instead of being passed down from parent to offspring. And in this case, by identifying 17 of these gene swaps, the team then established a kind of a rule of succession. If the gene jumped from lineage A to lineage B, lineage A must be older. And then they essentially did this for all of the known fungi species and tried to approximate the age of the oldest lineage, or basically the age of the oldest fungal gene. And so by using this particular molecular clock, they estimated that the common ancestor lived approximately 1.4 to maybe 0.9 billion years ago. So not as old as 2.4 billion years ago, but definitely much older than previous assumptions. This was during the so-called Proterozoic, representing one of the longest eons in terms of geological timescales. And though during this time most of the life known to us was largely aquatic, we also know that the surface contained one supercontinent referred to as Rodinia. But the atmosphere was generally oxygen poor, and intriguingly days here were approximately 18 to 19 hours long, not 24 like today. But previously it was assumed that the surface was mostly rocky and desert-like, and did not contain any complex life forms. As a matter of fact, this is also the period that's sometimes characterized as being the boring billion, because we don't usually find a lot of fossils around this time. But it looks like that assumption was possibly incorrect, because now we have at least several studies suggesting that fungi were probably already here and were probably doing something. And that's of course the next question. So what were they doing? What exactly were these ancient mushrooms doing on this barren planet? And in this case for at least 500 million years before the arrival of the first plants. Well, right now we think that they were basically preparing the stage, or preparing the meal for the rest of life that eventually settled on the planet. And that's because for billions of years, the terrestrial part of the planet, or basically the Earth's continents, were extremely bare and contained almost nothing except for rocks and shifting sand. So there was no soil, and there was nothing for life to live off. Yet here, ancient fungi, very likely in partnership with some of the primitive algae, eventually created the first true ecosystem on the surface. And so basically they became the ecosystem engineers. And so here, for millions and millions of years, they secreted powerful enzymes that eventually broke down a lot of solid rock and started to recycle nutrients like phosphorus and nitrogen, with this very long process eventually creating some of the first soils, and of course fundamentally altering the environment and possibly even the color of the planet. And so by the time the first plants were ready to move to the surface 500 million years ago, they did not come to the wasteland and instead landed in a world that was almost perfect for them because of these ancient fungi. And since the first plants did not even contain any true roots, they could only survive through the process known as mycorrhizal symbiosis, essentially a partnership between fungi and plants that helps them absorb nutrients from the soil. And this is of course something that a lot of plants, actually 80% of all plants, still rely on today. Basically every major tree and every major plant that contains roots will usually contain a huge network of fungi inside of them, responsible for extracting a lot of stuff plants cannot do themselves. And as a return, fungi get a lot of different sugars and basically free energy from the plants that can photosynthesize. And so here this was possibly the formation of this ancient partnership, with fungi eventually becoming an important part of many different plants. But when it comes to fungi, there's actually something else that's kind of fascinating about them, and specifically when it comes to their evolution. Whenever our planet faces one of the global extinctions or global catastrophes, a lot of fungi tend to see this as a new opportunity. And so, for example, during the Permian-Triassic extinction 252 million years ago, which was one of the worst extinction events on the planet, here, based on a lot of fossil records, we can actually see a massive fungal spike, as reported in this Berkeley study from 2011. And so, following many different extinctions, fungi once again become the dominant life on the planet, mostly because there's a lot of dead matter for them to survive off, and they don't really need sunlight or even stable temperature conditions in order to survive. I mean, if you have mold in the house, you know how difficult it is to usually get rid of it. And well, mold is a fungus. So a lot of fungi, they basically thrive where no other life can survive. And we of course saw this again 66 million years ago when the asteroid killed the dinosaurs. As many forests perished, the entire world became a kind of a massive compost heap, which once again allowed fungi to flourish and allowed them to recycle a lot of matter, rebuilding the foundation for the new world. As a matter of fact, unlike animals and plants, and even unlike certain other organisms, a lot of the genetic data shows us that fungi tend to actually not even care about mass extinctions and do not suffer from them at all. I mean, obviously the mushrooms that were living under the asteroid impact most likely perished, but all of the other ones living elsewhere were totally fine. They regrew very fast and recolonized the planet within just years. And well, by itself, this definitely presents mushrooms or fungi in a completely different light. Or basically, they're not just decomposers and they're not just something you put in your omelette, but they're possibly some of the most important complex life on the entire planet and very likely set the stage for everyone else to eventually start living on the surface. And though they do show up at the end of the life story, especially during the extinction events, they also seem to be the main architects that began everything on the surface. So basically all of the soil we rely on potentially came from these little guys. They enabled the evolution of plants, they allowed animal life to eventually settle on the surface, and they continuously survive every major disaster. And of course spoil our bread and make our bathrooms smell like mold. But that's a different story. They're still pretty cool though. And so trying to understand their evolution is not just some kind of a trip into the past, it's also a tool to help us understand what life needs to survive, or what we might even discover on some other planet somewhere out there when looking for some kind of a biosignature on a different planet. And so if we do find life on a rocky planet somewhere out there, it might not actually be green at all. Instead, it might contain certain chemical signatures produced by some kind of an alien fungus, as they're essentially transforming the surface just like they did on planet Earth. But in any case, this is definitely a somewhat intriguing study, and is definitely changing our perspective and the overall understanding of this boring billion that we previously knew very little about, and especially because fungi previously have always been a little bit underestimated. And so there's a very high chance that it was actually because of these little guys that the world became habitable. Hello wonderful person, this is Anton, and today we're going to discuss a somewhat exciting study about something that happened to planet Earth approximately 445 million years ago. Something that resulted in a kind of a turning point for the entire planet, and the event that resulted in the evolution of one of the most complex types of life on the planet, the vertebrate life. Or to be more exact, our ancient ancestors. All of the complex life that contains a vertebra was surprisingly a result of this one very specific event that also caused one of the biggest extinction events in history. And so in this video, we're going to talk about what's known as LOMI, or Late Ordovician Mass Extinction Event, and the creation of life as we know it. With all of this based on this recent study you can find in a description that discusses this mass extinction and the sudden explosion of certain types of life that became extremely common afterwards. But first, let's actually cover the basics, because this particular extinction event was absolutely enormous, and actually much bigger than the one that killed the dinosaurs. This much earlier catastrophe was the first of these so-called Big Five extinctions, and remains the second largest ever in terms of percentage of life lost. Here's roughly how it compares to other extinction events, including the one that killed the dinosaurs. But to understand why this happened and what happened, we basically have to look at what Earth looked like approximately 450 million years ago. And well, this is the so-called Ordovician period. During this time, the planet was a greenhouse. And at that time, almost all of the life lived in the oceans, which is of course where most of the extinction happened when it happened. But a lot of recent studies discovered that this was not just some kind of a major wipeout, this was actually a kind of an ecological reset. A reset that allowed our ancestors, the jawed vertebrates, to finally step out of the shadows and become a predominant species. But Earth back then also looked very different. Here it was mostly dominated by supercontinents, and the most famous one was Gondwana. It was located in the southern hemisphere and resembled something like this. But it was also surrounded by an enormous ocean. But unlike today, this ocean was not dominated by fish, and instead by creatures referred to as conodonts, primitive eel-like animals with very complex teeth that resemble something like this. But there were also a lot of giant shelled animals, such as nautiloids, that in some cases could grow up to about 5 meters long. One of the more famous ones is this one known as Cameroceras. And so as you can imagine, back then the oceans were extremely different. Naturally, the oceans contain a lot of other animals, including trilobites and sea scorpions, and a lot of other alien-looking species. But what about fish? Well, we know that fish that had jaws already existed. But unlike today, they were basically underdogs. They were extremely small in numbers and were mostly on the bottom of the food chain. But that's until this event 445 million years ago. Because here the environment suddenly started to shift. And it seems to have happened in two deadly pulses. The first one was triggered by a sudden glaciation, and to be more exact, a global ice age. And so here, as glaciers spread across Gondwana, they locked away so much water that the sea levels dropped significantly. And this ended up draining a lot of shallow coastal seas where most of the initial life flourished. And this already gave a lot of jawed fish just a little bit of an advantage, mostly because they preferred deep oceans. But then, several million years later, the second pulse hit as well. The climate shifted back to a warm state and the glaciers suddenly melted. And while you may think this is a good thing, it was not a good thing for a lot of sea life. And that's because all of these oceans became flooded with water that was low in oxygen and very high in toxic sulfur, essentially creating conditions inside the water that were extremely inhospitable to most of that ancient life. And so this double event of freezing then suffocating was just a little bit too much for the dominant species of the time, with approximately 85% of all of them eventually becoming extinct. Which brings us to this recent study from 2026, because here they discovered something else very important. And that's because for a very long time paleontologists were a little bit confused by this very bizarre gap. There was actually approximately 50 to 100 million year gap in the fossil record. Now we knew that jawed vertebrates existed, but they didn't seem to become diverse or dominant until much later, specifically in the Devonian period, or the so-called Age of Fishes. And it wasn't actually clear what was happening during these 50 million years, and why exactly it took so long. Which is where this team, led by Professor Lawrence Allen and Wahei Hagiwara, compiled a massive database of approximately 2,500 species in order to see how vertebrates reacted to this particular extinction. And what they discovered was fascinating. Now, before the extinction, the oceans were generally saturated with a lot of these jawless conodonts and quite a few large invertebrates. And so there was basically no room for a lot of these jawed fish to move in. But once these extinction pulses began, they slowly started to remove these dominant species, with the survivors being pushed into isolated regions of biodiversity in very specific niches where they could still thrive. And one of the most important such regions turned out to be in South China. And so here in these very isolated pockets, jawed fish did not have to compete with giants anymore, and they managed to find individual niches and even empty niches that were left behind by previously extinct animals. But because they were trapped in these very small geographical areas for millions of years, it was here that they started to diversify and specialize. Here it's even compared to the Darwin's finches on the Galapagos. And so this study discovers that during this extinction event, it was literally a kind of an ecological reset. And so even though vertebrates without a jaw, or jawless vertebrates, still dominated the oceans for at least 40 more million years, the jawed vertebrates, or basically fish, started to already diversify and become better and better in very specific locations where they became dominant. And it was here that they very likely developed the ability to eventually cross oceans. And so following millions of years of isolation, they were eventually able to enter other oceans and then spread like wildfire. And this period of low biodiversity is sometimes referred to as Telemas Gap. It was essentially this period of approximately 3 to 10 million years, during which time there was not a lot of species on the planet. But that's because apparently they were all hiding in extremely specific niches. And once they learned how to cross these niches, the true recovery finally began. Our ancient ancestors, the jawed fish, and so yeah, this right here is probably your grandma or something, finally started to take over the oceans and then eventually evolve into other things as well. And so the reason this particular study is kind of important is because it finally explains what seems to have happened on the planet and how it suddenly led to this transition 450 million years ago. In other words, it explains why in our history the jawed vertebrates appeared so suddenly and why they ultimately prevailed. And the answer in this case seems to be twofold. First, that ice age that emptied the oceans, and then the melting that introduced a lot of toxic stuff that basically killed a lot of their competition. And so if it wasn't for these two events, the oceans would still be ruled by a lot of unusual giant nautiloids and a lot of eel-like conodones. But more importantly, this research also confirms something really important about evolution. It essentially suggests that evolution follows a kind of a diversity reset cycle, with mass extinctions being extremely important for the constant evolution of complex life. And that's because extinctions do not actually erase life, they just kind of restructure it. They make animals that were probably hiding somewhere become dominant by giving them a new chance. And that's exactly what happened to mammals right after the age of dinosaurs. So basically, during the age of T-Rex, mammals were extremely small and very insignificant and were mostly hiding in various niches. But once dinosaurs disappeared, mammalian life took over and became widespread everywhere. And so here, every single extinction event removed the weaker dominant species and gave a chance to a smaller, more innovative group that eventually takes over. But in the end, all of us, including you and me, were basically the descendants of those few survivors from those ancient oceans. The survivors that were thriving in the coastal areas of South China Sea, waiting for their chance to rebuild the world's ecosystems. And that's a very important reminder that even some of the most catastrophic events on the planet end up setting stage for completely new paths for different types of life. So normally when we discuss geology, we're talking about processes that take millions if not billions of years. And that's because on Earth this involves cycles that are extremely slow and are very difficult to observe on human scales. For example, we have sediments that gets buried, gets compacted, and slowly cemented over eons as it transforms into some kind of a new mineral, thousands of which have developed on Earth in the last 4.5 billion years. And though for the most part Earth's crust is composed of silicate minerals, including quartz, feldspar, olivine, and mica, we also know that in the last 4 billion years, at least 2/3 of all minerals on Earth were actually created as a result of life, either directly or indirectly. Nearly 4,000 mineral species have been created as a result of various oxygenation reactions and as a result of biomineralization. And that actually includes over 90% of uranium-based minerals and even minerals containing nickel, cobalt, and molybdenum. And obviously all of the carbonate minerals like calcites were also formed by various types of life. But once again, these are processes that are pretty slow and take at least a few millions of years. Except that recently researchers discovered something that was officially created by humans and surprisingly happened pretty fast. Here researchers discovered something that might actually require us to rewrite textbooks on geology. It turns out that completely by accident, humans created a kind of a fast-track geology, forming a new type of a mineral in just 35 years. And here this is not just some kind of a curiosity, this is a new scientific classification for what now is referred to as anthropoclastic rock cycle. Something that was thoroughly explored in the study you can find in the description. And so today we're going to discuss some of these new discoveries and talk about these human-made rocks and discuss the science of how they are able to form so quickly and what this means for our understanding of Earth's history, and specifically the newly proposed Anthropocene epoch, something we've already discussed in one of the previous videos in the description. But one of the most recent and perhaps the most startling discoveries came from a coast of England, and specifically a place you see right here, the Derwent Howe. And so here a team led by Dr. Amanda Owen from the University of Glasgow discovered that the shoreline there is no longer formed by loose pebbles and sand. Instead, they discovered something entirely different. Here they found glassy blue-gray cliffs and hardened platforms made of what looks like natural rock. But this is not natural sandstone. It's actually what's known as steel slag, waste material from various industrial furnaces that have eventually fused into a lot of this solid stone. And that's because for approximately 200 years, industrial activity in England, and especially at this site, dumped a tremendous amount of waste, depositing it in the soil, with the ocean waves then sculpting this waste and cementing this inside the rock. But I guess one question here is, okay, but how do we know this is what happened, and if this happened fast? Well, geologists don't just guess. They look for what's known as index fossils, or markers. And in this case, the markers weren't trilobites or dinosaur bones, and instead they were actually pennies. You can see them in this image. These were King George V pennies from 1934, and even more specifically, an aluminium pull tab from a can that was only launched in 1989. But because these objects were found inside rock, and specifically inside solid rock, scientists can now confirm that none of this took longer than 35 years. Once again, because the youngest object was from 1989. And in geological terms, this is essentially instantaneous. And there are quite a lot of images you can find of this on the web, showing us how the rocks in this region look entirely different. And so here we have a lot of examples of industrial waste literally becoming rock. But I guess the question is, how? How does a pile of industrial trash become a cliff in just 3 decades? And that's of course quite a big mystery, because normally, in natural sandstone, grains of sand must be buried deep underground first, and they then have to be squeezed by pressure before they slowly get glued together for millions of years. And well, the answer seems to be that glue. In this anthropoclastic rock cycle, the glue seems to be pre-mixed in the waste. And mostly because a lot of stuff that was deposited here already contained many of these particles. And specifically when the team from Glasgow analyzed the section of the rock, and used tools like, for example, X-ray diffraction and Raman spectroscopy, they discovered a lot of familiar minerals, calcites, brucites, and goethites. And these are actually exactly the same minerals you usually find in a regular sediment that were already forming here as well. But the difference is the starting chemistry. In a typical steel slag, it's actually already chemically primed for the cement growth. And so when it reacts with seawater and the atmosphere, it generally creates rapid chemical bonds that then mimic natural lithification. Or basically they kind of look like natural rock formation, but at extremely fast scales. With this process then turning sediment into stone thousands and thousands of times faster than in nature. But turns out that this is not just happening in England, although that part is maybe not very surprising. This is now happening pretty much everywhere. But right now, a survey of 14 British sites already found approximately 76 miles of these coastal slag deposits that have been officially confirmed. But they've also been spotted in Baltimore and in Bilbao in Spain. And the thing is, it's obviously not getting any better. Steelmaking now produces approximately 2 billion tons every year, which then results in approximately 400 million tons of slag. And all of this gets deposited somewhere. And turns out that all of this steel slag then starts to form these rocks in just a few decades. Although I guess just to clarify, steel slag is basically a byproduct of steelmaking that usually separates molten steel from impurities. And so at the end it usually forms a kind of a silicate and oxide-rich material that then becomes solid once you cool it down. And though sometimes it can be used in constructing roads and in even making concrete, for the most part it just ends up like this. It's just dumped somewhere and left alone. But it's not only about metal slag, or basically it's not just about steelmaking. Because turns out humans have accidentally found another way to make a different type of minerals. And you might guess what's in it. Plastic. So we now have a new thing called plastic glomerates. Literally a rock containing a lot of plastics. And this was first documented on Camilo Beach in Hawaii only in 2014. And so basically these are rocks where plastic waste, for example fishing nets, ropes and containers, start to act as a binding agent and create their own mineral as a result. And when this plastic is melted, for example by campfires or even volcanic heat, it then flows into gaps between sand, seashells and coral, mixing everything together and literally creating a new type of mineral. And so once everything cools down, it essentially creates a kind of a junkyard mixture. Something that's a lot denser than normal plastic, and also something that's pretty heavy. And because it's heavy, many of these plastic glomerates eventually sink to the seafloor, where they can then significantly increase the chance that they're going to be buried and preserved in the geological record. And so here scientists like Patricia Corcoran discovered these unusual minerals at pretty much every site in Hawaii, with this report in 2020 officially coining the term. But since then they've been reported in most locations on the planet, including Indonesia, Brazil and Japan. And so even though this was the first official site, they've now been confirmed to exist worldwide. And this is officially becoming a kind of a global marker for that previously mentioned Anthropocene, a proposed geological epoch defined by direct human impact on planet Earth. And so in pretty much all cases here, this is something that's formed by human activity, and in this case plastic waste that was melted over time, that once again starts to somehow cement surrounding natural materials, but in this case doing so extremely quickly, eventually resulting in these unusual rocks. And we now know that this can actually form naturally, where plastic pollution can then meet some kind of a heat source, such as lava flows or forest fires. which is why it was discovered in Hawaii, very close to volcanic activity. And so because of their durability and high density, researchers now believe that these are basically technofossils. They're extremely likely to persist for millions, if not billions of years, serving as a kind of a permanent physical signature of human pollution. And though it is quite possible that some of this might convert to something else, even reverting back to oil form, this still doesn't change the fact that this is an incontrovertible evidence of human presence. With this type of a mineral even having its own subforms now, such as plastic crusts and plastistones. Basically slightly different formations depending on how they were formed and what's inside of them. And that's of course a really important reminder of something else. Plastic pollution has now reached pretty much everywhere, even the most isolated ecosystems on planet Earth. And we actually recently discussed some of the more dangerous parts of plastic pollution in one of the videos about human health that you can find in the description. But I guess the question is, so is this a problem though? Especially because this is basically maybe one potential solution to that plastic problem. Maybe by turning this into rock and by creating more plastic minerals, we can start solving the problem of plastic pollution on the planet. I mean, for all we know, maybe we can take a bunch of these rocks and then create some kind of an island somewhere. Hey, more land, more real estate, right? But the real answer is a little bit more complicated. And that's because a lot of these rocks also change the way coastlines work. For example, those metal-based rocks, or the slag aprons, generally change how waves reflect and how sediment moves in the ocean. And that can actually cause faster erosion on a lot of natural cliffs nearby. On top of this, there's also the obvious chemical component. Many of these rocks will contain something toxic inside. For example, toxic metals like chromium and vanadium. They can also create what's known as an alkaline halo. They essentially raise the pH level inside water, and that makes water more basic, which can then stress local wildlife and affect a lot of wildlife living nearby. Now, the actual effects have not been established yet, and this has not been studied that well, but there is a slight chance that it could be more hazardous. At the moment though, it's kind of unknown. But on the positive side, some engineers started looking at these rocks as potential sources of carbon sinks. And that's because in many cases, various chemical reactions, the reactions that actually create the stone, can also absorb carbon dioxide more efficiently, thus reducing the levels of CO2. But here we have to be careful obviously, because we don't really want to trade the carbon dioxide problem for a toxic beach problem. So this is something that has to be investigated in some of the future studies. But because many of these discoveries are essentially brand new and we're just learning about this, at the moment there is not much else that's known. I mean, we definitely have evidence of this rapid anthropoclastic rock cycle, the cycle that turns industrial and plastic waste into solid stone in just a few decades, but we don't really know what effect it's going to have on the planet and whether this is good or bad. We just know that this confirms that humans are definitely actively reshaping the planet, while also officially adding this little bookmark into the book of geology of planet Earth. And so here we have rocks that prove our industrial materials do not just sit in landfills, they do enter the rock cycle, becoming a permanent part of the Earth's crust. But here it would be interesting to discover how quickly nature adapts to all of this and how it's able to incorporate all of this waste into its own natural processes. Hello wonderful person, this is Anton, and today we're going to be discussing one of the biggest mysteries in science, the origin of life on planet Earth. And specifically some of the recent discoveries and some of the most recent research that tries to identify some of the earliest genes that existed on the planet and basically try to figure out how life might have started. Now, just so that we're clear, we still have no idea exactly how it happened, but because of these two recent studies we're going to be discussing today, researchers got just a little bit closer to understanding the process. But first, let's actually start with some of the things we already knew, and specifically let's start with LUCA. And that's because for decades researchers have been able to trace the history of life back to a single point biologists often refer to as LUCA, the last universal common ancestor. Basically some kind of a protocell or some kind of an early life that became so successful on the planet that it eventually evolved into bacteria and archaea, that then obviously evolved into everything else. But there's always been a problem here, because in this case, LUCA, which very likely evolved approximately 4.2 billion years ago, or approximately 300 million years after Earth formed, was already an incredibly complex cellular organism. it already had a genome, it already built proteins, and it already had functioning membrane. And we know all of this based on the genetic analysis of a lot of bacterial and archaeal cells, which seem to share certain genes that must have come from Luca. And so we know that this was a single-celled, prokaryote-like organism that used its own genetic material or its own DNA, and also very likely relied on the ATP for energy, and most likely lived in very enriched environments, such as near hydrothermal vents, in order to basically survive and in order to thrive. But since there are no actual fossils of Luca, we don't really know much else. And that means that Luca was not the first life, and instead was a very successful cell that eventually evolved everything else. And that means that we have no idea what the first life was like. And also because this was 4.2 billion years ago, the genes from this organism experienced what's known as horizontal gene transfer, or basically became shuffled in a lot of different organisms alive today. But even back in 2016, at least one study was able to identify 350 individual genes that most likely came from Luca, essentially confirming that this was an anaerobic organism, not relying on oxygen, and was also able to fix its own CO2 for energy and to build its own proteins, and might have also been able to fix nitrogen to create ammonia. And moreover, it also contained certain proteins that seem to protect it from viruses, implying that viruses were already attacking cells and were already driving evolution. But this is still an extremely mysterious part of history, and there are still a lot of unanswered questions about the overall transition from the very simple cells to much more complex cells. Something that we didn't really know much about until some of these most recent studies. And that's because these studies now provide us with new tools to try to analyze Luca and even analyze life before Luca in order to understand what happened during those first few millions of years. And so basically in evolutionary biology, one of the biggest mysteries is of course this pre-Luca era. The period before Luca was evolved, and the period that we know absolutely nothing about. And well, up until recently, it was practically impossible to analyze any of this, because once again there are no fossils, and even trying to analyze genetics was extremely challenging. But in this recent study, researchers found at least one intriguing technique that allows us to use this genetic fossil that's technically hidden inside our own DNA and basically DNA of everything around us. And so in this new study from 2026, by researchers Aaron Goldman, Gregory Fournier, and Betul Kassar, researchers focus on something referred to as universal paralogs. And in biology, the term paralog refers to a bunch of related genes within a single genome, and normally they're produced as a result of duplication. And the best example here is actually hemoglobin, or specifically hemoglobin genes. Humans contain 8 of them, and all 8 of them are just copies or descendants of the original hemoglobin gene that appeared approximately 800 million years ago. And so here the formation of this protein containing iron that then allows the blood to transfer oxygen first appeared 800 million years ago, and then eventually evolved and copied itself with many different species containing different versions. And once again, humans contain 8 of them. These are essentially paralogs. But the point in this research was to actually try to identify some kind of a universal paralog. So basically not just hemoglobin that only applies to animals containing blood, but something that's even more universal that pretty much all life on the planet would contain. And so here they were looking for a family of genes that seem to exist in at least 2 copies in almost every living organism on the planet. And that's because by finding these universal paralogs, or these genes that were basically copied into every living organism, we would then be able to identify original genes that must have duplicated even before Luca existed. And so these very rare genes effectively allow scientists to peer back in time and to try to see what life was like before Luca was around, and very likely right after life became extremely common, or at least extremely successful. Naturally, because these genes never died out and remain with us ever since. And here researchers do discover something. They found that all known universal paralogs seem to involve just 2 separate tasks. First one is building proteins. Okay, that one is kind of obvious. You need proteins for life to exist. But the second one is a little bit more exciting. It involves moving molecules across cell membranes. And that of course suggests that both building proteins and moving stuff across cell membranes seem to be some of the first and some of the most successful biological functions to ever evolve. Or I guess technically you can even define this as life. Maybe that's actually what the definition of life should be. And that, by the way, connects to this other question we tried to discuss in a previous video you can find in the description. Because even today it's not clear what exactly life is. But to make this even more interesting, researchers behind the study even performed an intriguing experiment. And specifically, they actually resurrected one of these ancient proteins from one of these pre-Leuca families, mostly focusing on the protein you see right here. And well, they discovered that even this ancient simplified protein was still able to attach to a lot of cell membranes and even interact with protein-making machinery, suggesting that this was indeed a universal protein that very likely exists longer than anything else. And this by itself is quite incredible because it definitively proves that cellularity, or the idea that the life seems to be contained inside a membrane, seems to have been established on Earth extremely early on, and was possibly the main reason life was so successful. Obviously because membranes in this case provide a lot of protection. And so it was probably the membranes that seemed to play the biggest role in allowing the life to become so successful. But this is just the first study and the first experiment, so we don't really know much else. But we do know something else from a separate study on RNA molecules. And this is based on a study led by Philip Holliger that was recently published in Science. And so basically here, even though the paralogs tell us a little bit more about how cells worked, it doesn't entirely tell us why cells existed or how the first genetic material even started to copy itself. And that's of course the other major problem. How did the genetic material evolve and where did it come from? And well, one of the most accepted propositions today is what's known as the RNA world hypothesis. The idea that before DNA and before proteins, most of life very likely relied on RNA in order to both store information and in order to create a lot of other stuff. But when it comes to this model or this hypothesis, there was actually at least one problem that was very difficult to resolve. All of the RNA molecules known to us that could actually polymerase, or that basically could copy other RNA molecules or produce proteins, were actually very large and very complex. And because they were so large and so complex, it was extremely unlikely that they would just appear out of nowhere in the primordial soup on the early Earth. So basically it was hard to explain how exactly did such a complex RNA even start. And so in this 2026 study, researchers decided to search through a massive library of different RNA sequences, actually involving 12 trillion different samples. That's trillion. That's a lot of samples. And in this massive library, they discovered a tiny molecule referred to as QT45. The RNA molecule you see right here, compared to a typical RNA that was only 45 nucleotides long and was exceptionally small for a typical molecular builder. As a matter of fact, it was at least 3 times smaller than a typical RNA. And because it was so much smaller, here it was extremely more likely to just spontaneously form just because it did not have as many units. But importantly, just like more complex RNA molecules, here it possessed very important functions. And so in this study, by mimicking conditions involving slushy, salty ice that might have existed on the early planet, researchers confirmed that this molecule can actually act as a polymerase and basically build additional strands of RNA that can then be used as a template to create brand new copies. And so basically it had what's known as synthetic self-synthesis. Although in this case, the optimal conditions involved slightly salty alkaline water and relatively cold temperatures. And that's actually a kind of a game changer, mostly because here we now have this very tiny molecule able to perform complex functions of replication without any complex machinery and without being massive, providing very important evidence for the RNA world hypothesis, and once again suggesting that life could have indeed started with these very tiny pieces of RNA, or basically suggesting that the life-starting molecules might have been very abundant and extremely common, and were just much smaller in size than we thought. And so in more biological terms, these functional polymerase ribosomes seem to be much more common and much simpler than biologists previously believed. And that was actually an important missing piece when it comes to the story of the origin of life. Okay, so why does this matter? Or I guess what's the actual conclusion? Well, by combining these two studies on the universal paralogs and the discovery of QT45, researchers are finally able to fill this 100 to 200 million year gap between the origin of the first habitable environments and the emergence of Leuca, something that was previously completely impossible. With these studies essentially providing almost direct evidence that life almost certainly did not just appear out of nowhere and did not start as a very complex cell, but instead began with these very simple tiny RNA replicators that eventually evolved the ability to build proteins and manage membranes, and then slowly started to create foundational systems that allowed Luca to thrive. And more importantly, both of these studies also provide all of the necessary conditions to turn this into testable lab experiments. Something that can now be confirmed or disproven, and something that I'm sure we're going to be discussing more in some of the future videos. But for trying to find life somewhere else out there, or for astrobiology, this is also really important because here we have several confirmations that generally requirements for life seem to be kind of simple and can potentially be easily created in a lot of other conditions. And so for moons like Europa and Enceladus, and obviously for other planets out there, this is maybe good news. But until we actually go somewhere else and try to find life there, we're not going to know if this happened anywhere else. Hello wonderful person, this is Anton, and today we're going to discuss some of the recent discoveries in regards to Earth's magnetosphere. And specifically, a somewhat intriguing simulation, or I guess sonification, that allows us to hear what Earth's magnetosphere potentially sounded like during one of the most important events in the last 42,000 years. The event when the Earth's magnetosphere dropped by a tremendous amount, during which time the magnetic poles almost reversed. And so let's discuss some of these new discoveries, starting with the discoveries from billions of years ago. And specifically, this study from just a few months back. Here, we finally have some of the most exciting evidence in regards to the early magnetosphere. This is coming from rocks that were formed 3.7 billion years ago, discovered in some of the deposits in Iceland. With these rocks formed during the Archean Aeon, revealing something we always suspected but could never prove. These rocks definitively contain signs of an early magnetic field, discovered in a very similar way how we usually discover these signs in much more recent deposits. This was basically the result of magnetite being deposited in a very certain way as various magnetic sediments follow the magnetic lines, creating various magnetic phenomena inside the deposits. And what's really exciting here is that the scientists can even determine the overall strength of the magnetosphere, with these samples suggesting that the magnetosphere was not actually that weak. Here the strength was approximately 15 microtesla, and this was 3.7 billion years ago, which is only half of what it is today. The modern magnetic field is approximately 30 microtesla. And so even on this early Earth, the magnetosphere already existed and was already pretty strong. But not as strong as today, and as a result, the scientists in the study actually suggest that it might have produced very specific effects. It obviously protected Earth, but did not protect it enough. And so here, because the protection from the solar wind was a little bit less, with the level of protection increasing in the last few billions of years, it possibly resulted in a dramatic loss of different types of atoms, for example, certain types of xenon and hydrogen. And so basically this resulted in a kind of an atmospheric escape that affected the atmosphere to some extent. Although what effects this had on life on the planet and the eventual evolution of the atmosphere and the oceans is currently unknown. Nevertheless, discovering evidence for this early magnetosphere is super important, because it basically confirms what we always believed. This magnetosphere is very likely one of the main reasons life was able to secure itself so early on, and why it was able to evolve, because all of this obviously protected the planet from additional atmospheric loss and from very powerful radiation coming from outside. But in terms of magnetosphere protecting life, there are still some unanswered questions and obviously some mysteries. And one such mystery comes from a different study. A study by Juan and his team, released in May of 2024, on the near collapse of geomagnetic field during Ediacaran period. The period famous for the existence of a lot of very unusual life, during which a lot of life evolved super quickly. And so here we have even more evidence for something unusual that happened during this time. This happened approximately 590 million years ago, and was essentially a near collapse of the magnetic field lasting for approximately 26 million years. And so basically here, by studying additional magnetic deposits, researchers discovered that between 591 and 565 million years ago, the magnetic field was about 30 times weaker than today. Today this is referred to as ultra-low time-averaged field intensity, and it's currently difficult to explain. But what's even more difficult to explain is what actually happened to life. Because life did not go extinct during this time, but potentially experienced something that's almost the opposite. Even though during these 26 million years there was very likely a lot more radiation on the surface, for some reason the oxygen levels dramatically went up, suddenly creating conditions where life could now evolve a lot of complexity and could now thrive to be multicellular. And so during this time there was a huge surge in atmospheric and oceanic oxygen, which lasted for approximately 10 million years, but more importantly resulted in a major explosion of biodiversity. This is often referred to as the Ediacaran explosion, and we've actually discussed it relatively recently in one of the videos in the description. And so during this time there was an appearance of a lot of complex ecosystems and a lot of relatively complex animals, all of this coinciding with very high levels of oxygen, but all of this basically kind of stopping when the magnetosphere returned back to normal levels. And so here it's actually unclear exactly what happened, but the evidence seems to suggest that relatively low levels of magnetosphere, which basically resulted in a much higher radiation on the surface, for some reason helped life become more complex instead of causing a typical extinction event. Which naturally suggests that we still don't really understand exactly what the magnetosphere does for life on the planet, and exactly how it protects the surface or how it protects life. But all of these events happened a long time ago. What about slightly more recent times? Not millions of years ago, but instead thousands of years ago. Well, when it comes to more recent events, there are two types of events researchers are super interested in: the reversals and the excursions. Now, we actually have a lot of evidence for reversals that seem to, on average, happen every 300,000 years. And this is basically when the north and the south magnetic pole sort of switch places. But during the reversal, which can actually last for thousands of years, the magnetic field also kind of weakens, and the north and the south pole instead become multiple poles. And the last such event most likely happened 780,000 years ago. So technically we're a little bit overdue for the next reversal. But we know that for life, these events don't seem to really do much. We know that a lot of life, including our ancestors, lived through a lot of this without any issues, and they don't seem to correlate with any major effects on the atmosphere or on the climate. But if such an event were to occur today, it would definitely affect our technology. So obviously things like satellites and telecommunication would suffer quite a lot. But as I mentioned, reversals are not that common. They basically happen every few 100,000 years. But there is a different event that's slightly less predictable and potentially just as extreme. These are known as excursions. And the last excursion was a lot more recent. It basically happened when humans already existed, occurring approximately 41 to 42,000 years ago. And this one is really famous and has a name. It's known as the Les Cham excursion or the Les Cham event. This is something that very likely lasted for approximately 250 years to maybe 440 years, during which time the magnetic field also dropped quite dramatically, going down to about 5% of its current value, and resulting in a partial reversal of the poles, which then returned back to normal. And during this event, for about 500 years, it looks like the magnetic field was about 5 to maybe 25% of the current value, resulting in a much higher radiation on the surface, as recently discussed in one of the studies. And so during this excursion, when there were basically several poles instead of just one pole, researchers discovered definitive signs of various isotopes, specifically cosmogenic radionucleotides like beryllium-10, which can only be formed when there is more cosmic rays coming from outer space. And this normally tells us how strong the magnetic field generally is. And so here the evidence suggests much lower field for approximately 500 years. But more intriguingly, this unusual event correlates with a few things that happen on the planet. For example, we know that during this time, our friends, or technically our cousins Neanderthals, seem to have disappeared. And at the same time, a lot of cave art started to appear in various locations. Now this is obviously just a correlation, not a causation, but it is intriguing nevertheless. And so one implication here is that it might have actually helped our species to somehow become more dominant. But exactly why this would affect Neanderthals and not humans is of course unclear. As a matter of fact, a lot of scientists actually think that this is maybe just a coincidence. Nevertheless, the increase in beryllium-10 definitively suggests much higher cosmic rays, and of course much lower magnetosphere. And so in one of the recent studies, researchers actually did something really cool. They basically sonified it, allowing us to hear what all of this potentially sounded like if we could actually somehow hear the magnetic field. And so here, by using the data from the ESA's SWARM mission, which is essentially 3 satellites that monitor the magnetic field by orbiting the planet, researchers were able to create a kind of an unusual animation, or technically sonification, first showing us how the magnetic field most likely sounded for the past 100,000 years. You can listen to this in one of the links in the description, but then creating the sounds of the Le Cham excursion. And so here, because we can't really see the magnetic field, in this case, we can hear it, with these audio clips essentially showing us how these fields would sound differently if we could somehow detect these magnetic lines with our ears. And this is of course something that a lot of animals out there can kind of do. A lot of animals can sense the magnetic fields, and so for them this is maybe not something unusual. And so in this case, this clip, and here I'm only going to play a small part of it, allows us to imagine what it might be like to hear these excursions if they were to occur right now. Although in this case this is more of an artistic representation because this lasts for 3,000 years. But more importantly, one of the reasons for these studies is to definitively show us that it's unlikely that anything like this is happening right now, unlike previous claims from the press that suggested that the magnetic field might actually flip really soon. As a matter of fact, the magnetic field seems to be as strong as ever, and is not showing any signs of flipping or even starting these excursions anytime soon. Obviously though, we want to understand what would happen if this did occur, or how to detect these events when they're about to start. But as I mentioned, excursions and reversals are very different. Reversal results in a permanent change of the poles and usually lasts for thousands of years. Excursion only produces temporary changes and lasts for only a few hundred years. But both events result in the weakening of the magnetosphere for at least some time. But just to summarize all of these studies and to basically come to some kind of a conclusion here, well, the conclusion is that we still don't really understand magnetic fields very well, or at least their effects on the surface of the planet. Because here the evidence suggests that, yeah, it can affect life, we just don't really know in what ways. And more importantly, it doesn't really seem to have an effect on human life, but it will probably have an effect on our technology. But it looks like nothing like this is happening anytime soon, and so for at least a few hundred years, we can definitely rest. Hello wonderful person, this is Anton, and today we're going to discuss a somewhat bizarre mystery that appeared on our planet approximately a decade ago. And specifically very unusual holes, one of which you can see right here, that suddenly appeared in the ground in certain locations in northern Russia. But specifically, they seem to be formed by some kind of an incredible explosion, with tons of soil and massive blocks of ice hurled hundreds of feet into the air. But these were not volcanic eruptions and not results of meteor impacts, or some bizarre military tests by Russia or aliens, because it turns out that these were actual physical phenomena that are now happening because of the thawing of permafrost in some very specific locations. And so technically this is now referred to as GECs, giant gas emission craters. Super mysterious formations that were very challenging to explain for over a decade, and first spotted back in 2012 in very remote parts of western Siberia. And intriguingly, if you go on Google Maps, or Google Earth in this case, you can actually find them and you can see them yourselves, with I think this one right here, known as the Yamal crater, being the most famous one. And so because this was such a bizarre discovery and because we've never seen anything like this, back in 2012 this kind of became a global sensation. But mostly because of what they were like. First of all of them were near vertical structures and cylindrical in shape, and very often at least 50 meters deep. But more importantly, this was an indication of something ridiculously powerful, and something we've obviously never seen before. But here there was a central puzzle. Why exactly do these unusual objects, these GECs, only form in this very specific region, essentially limited to this location right here, the Yamal and Gaidan Peninsula? And for some reason they were not visible anywhere else where we detect permafrost, and where we technically expect something very similar. And so none of the other Arctic regions seem to have these. And so if this was, for example, the result of, I guess, global warming, why only here and why nowhere else? And well, this is the mystery we're going to be discussing today, because it looks like it was finally solved in this recent study by Helge Hellevang and the team you see right here. And this was on the formation of giant Siberian gas emission craters. And so today we're going to look at what we know about these geological events, why they happen where they do, and why they're also an important indicator of much larger changes happening to our planet, and I guess what's going to happen next. But first, I guess let's discuss some of the previous propositions. And so for many years, previous models tried to explain these objects using processes that seem to happen within permafrost layer itself. And many of these propositions very often focused on the idea known as talic. Talic refers to a kind of a historic lake created in the thaw zone, or the unfrozen ground within permafrost, that some studies suggest traps a lot of different gas from a lot of thawing ice and then dissolves various hydrates, which create certain chemical reactions. But this didn't really explain everything. Here there was actually a major drawback. Features like ground ice and additional features known as cryopags, or pockets of very salty water, are actually quite widespread in many Arctic locations. They're not just present here. And so if all of this was the result of some kind of a lake interaction, or something in regards to super salty water, these GECs should be forming pretty much everywhere where we have permafrost. Yet they weren't. Something very specific was happening in Yamal and Gaiden regions, and something that could not just be explained with these underground lakes. And so I guess what makes these regions so unique? Yamal and Gaiden regions. Well, there are actually quite a few features that make these regions quite unique. For example, enormous gas deposits. This particular area of West Siberia is what's known as a hydrocarbon province. It contains a lot of natural gas resources, with the Yamal Peninsula alone containing 26 trillion cubic meters of gas. And it just so happens that a lot of these bizarre structures are often found in proximity of a lot of active gas fields. Then there's also something related to geological heat and geological faults. And because of this, in this region, the permafrost varies strongly in thickness. Sometimes it's up to 500 meters, but sometimes it's only a few tens of meters. And so because of this potentially forms very specific geological weaknesses or geological cracks that seem to run deep into the earth, with many of these faults acting as pathways. And these deep faults bring two crucial ingredients to the base of the permafrost. They bring natural gas and heat. So basically they act as a kind of a funnel where a lot of this gas and heat suddenly accumulate because of the permafrost structure underneath. And so the sudden influx of gas and heat from deep below starts deforming and melting the bottom of permafrost, especially in the locations where it's naturally much thinner. And though this process usually takes at least a few years, eventually develops a dome of gas and a lot of heat right at the base of this relatively thin permafrost, with this permafrost basically acting as a kind of a lid, but in this case, a lid that's only a few meters across and that's much thinner than in other locations. With all of this sort of summarized in this new model for how all of this works. This is now the GEC formation model that's basically described in this paper, and here there are four main stages. First, the building stage. This is when natural gas from underneath slowly migrates underneath the ground and starts to accumulate in certain domal structures, with the additional heat that usually travels along with it, causing some of this permafrost to start thinning even more and to start slowly melting. Naturally, this leads to overpressure underneath, but only in very certain locations. Then we have the second stage, or I guess the second step, the catastrophic failure. And in this case, it seems to be the result of the global warming. So basically here, the global climate change comes into play. Because the average temperature in many of these areas has been rising, this permafrost seal starts to thin even more, which slowly makes the gas underneath, the pressurized gas, move closer and closer to the surface. And when the pressure underneath is too great and the permafrost itself is too thin, the seal can no longer hold, with the mid part of the seal failing explosively, releasing fluids, ice and sediment into the air. And here we're talking about massive forces. This basically results in a relatively large explosion, with huge chunks of ice up to 1 meter across, dramatically ejected around the crater. And that's of course what's observed in most of these locations. But furthermore, the rapid release of gas from saturated waters creates a kind of a champagne effect that drives even more mass out of the crater, which eventually leaves behind a near perfectly cylindrical structure that's essentially been observed in many of these locations. But that was just the first two steps. Then we have step 3 and step 4, which happen after the eruption. And so now this crater, that's essentially just a hollow depressurized space, can no longer carry the weight of the surrounding layers, leading to further collapse and the formation of concentric folds around the edge. And that's something you see very well in this picture. And during the final step, the crater fills with sediment and water and basically becomes some kind of a lake, with this whole structure now turning into peat. And so over time they begin to look like ordinary thermokarst lakes, lakes that usually form from thawing ice, which also suggests that the true number of these structures in reality might be much higher because many of them potentially already became these lakes and just look a little bit different. As a matter of fact, here on the map you can actually see quite a lot of very similar structures that do resemble circular lakes that might have started as these explosions. But according to this study, this is not the end. As a matter of fact, there is also a chance that this might happen again, as in the system can actually recharge itself, because the gas in this case is still going to be migrating underneath, and if permafrost regrows itself in certain locations, it can actually create another seal, allowing for more pressure to build up in the future, and for this process to repeat again. And so all of this can be basically summarized in this picture right here. We have the eruption stage, followed by the masking stage, which can technically become the eruption stage again if this permafrost forms a new seal. But I guess the question is, so does this actually matter, and what is this showing us? Well, the thing is, these GECs are a direct, visible, and violent manifestation of a much larger effect, the permafrost degradation driven by climate change. And that's because, generally, the Arctic permafrost acts as a colossal freezer that normally stores huge amounts of hydrocarbons. But when this permafrost starts to thaw and starts to degrade, and as it starts releasing these trapped gases either through explosion or just by seeping through, it starts to release a lot of gases that have been trapped in there for thousands and thousands of years, and one of the primary gases it tends to release is methane. And it just so happens that not so long ago, we've discussed a sudden dramatic increase of methane that was actually not accounted for, and there's a very high chance it's possibly coming from this permafrost from a lot of these locations where it was basically hidden for thousands of years. And it just so happens that methane is an extremely potent greenhouse gas, which means that it might actually create a feedback loop where more methane causes more permafrost to melt, which leads to even more methane being released, with the cycle repeating itself many times. And so the main concern in this case is this bizarre positive feedback. If the permafrost keeps thawing and releasing more gas, it will be almost impossible to stop this, just because it's essentially a kind of a self-sustaining mechanism. And in this particular case, these structures essentially show us a kind of a permafrost failure, possibly showing us some of the first indications that we're about to enter a new climate era. But based on the study, we can also assume that these GECs also formed sometimes in the past, and specifically during past warm periods such as the Holocene climate maximum 8,000 years ago, which may have produced very similar structures, and which are now possibly just a bunch of lakes in this region. And so by learning more about what happened in the past, in order to understand what we might have to deal with in years to come. And so by understanding the specific mechanism for these GECs, this might help us prepare for the climate change a little bit better. But I guess in summary, so at least now we know these are not just some random explosions, and seem to be a direct result of very deep geological interactions involving gas, heat, and thawing permafrost, but also an event that seems to be accelerated by modern atmospheric warming, and possibly something that happened in the past, and something that's going to happen even more frequently in years to come. Hello wonderful person, this is Anton, and today we're going to be discussing a topic that has long been considered to be kind of on the fringe when it comes to mainstream geophysics, and specifically the topic of earthquakes potentially connected to solar emissions or solar activity. But in this video we're going to discuss some of the more recent studies and some of the more recent analysis that once again presents us with a slightly more complex picture, and even presents a new connection between our Sun and earthquakes on planet Earth, or specifically seismic activity. And by itself, this is mostly a controversial topic because most geophysicists today still don't actually think there's any connection. As a matter of fact, the main consensus is that there is no meaningful link between solar cycles and earthquakes. However, it's still worth discussing these two new studies, and actually studies released very recently, that suggest that there might be some connection and that the Sun might be nudging our planet in just the right way, forcing certain physical mechanisms to then cause earthquakes. But to start, let's actually begin with what most geophysicists believe and why they think so, because here the point is pretty strong. And so based on the traditional view, the US Geological Survey maintains that earthquakes do not follow any solar activity at all, or at least don't follow solar activity in a predictable way. And specifically they're referring to the 11-year cycle. And essentially I think this image kind of summarizes everything really well. Every 11 years our sun goes through some major peaks. A lot of solar activity, a lot of sunspots, and lots of geomagnetic emissions. And if there was any connection between solar activity and earthquakes, we would actually expect more earthquakes every 11 years as well. But no such connection exists, and earthquakes generally happen relatively randomly. And so normally scientists are pretty cautious when trying to make any predictions because solar flares, geomagnetic storms, and earthquakes are relatively common events, and so if you do wait long enough, some of them will obviously coincide. But this is just sheer coincidence. But in these two new studies we're going to be discussing now, scientists took a slightly different approach. Instead of just counting sunspots, they're now looking at actual physics of how energy is transferred from the sun to Earth's crust, in order to understand if maybe there is some effect after all. And mostly because even if we can find a kind of a small correlation, it will actually be a major breakthrough in trying to forecast earthquakes and thus save lives. And so, for example, the ability for scientists to somehow predict that during a certain week there might be a higher chance for an earthquake could save thousands of lives and billions of dollars in damages. Which is naturally why there are still so many studies coming out trying to find these connections. And so let's discuss the first one, or I guess the first proposed mechanism, the solar heat hypothesis. This is based on a study you can find in the description, and as the name implies, here researchers try to find a connection between the solar heat and the effects on the Earth's crust. And so here in the study from University of Tsukuba, scientists found that the solar activity seems to influence earthquakes through a surprisingly simple method, heat. And well, here's how this would work. Normally, solar activity drives a lot of changes in the Earth's atmosphere, and specifically the surface atmospheric temperature. And though the temperature change is not enough to influence the crust, it is enough to affect the hydrological cycle. And so when the atmospheric temperature shifts, it also changes how water evaporates, and obviously how snow melts, and how groundwater moves inside. With all of this then affecting the water seeping into faults and actually changing the overall pore pressure, or basically the lubrication, between various tectonic plates. With the scientists discovering that if you actually include the surface temperature as a variable, the ability to predict the maximum magnitude of earthquakes in the coming days seems to improve quite dramatically, and especially for some of the more shallow earthquakes less than 30 kilometers in depth. But on top of this here, they also discovered a kind of a delay effect. Or basically the solar changes and the temperature changes do not trigger quakes on the same day. Here the heat distribution can actually take weeks or even months to settle, naturally because all of this groundwater will usually take quite some time to reach the ground underneath. And so intriguingly, in certain regions like in the Balkans, the most accurate predictions happened when using solar data from 180 days prior. In other words, after seeing the solar activity and the effects on the atmosphere and basically shifting this by 180 days, the overall correlation or the overall ability to predict earthquakes seems to actually increase just a little bit. This was then assessed in a lot of other regions, and here there seems to be at least some correlation and at least some delay. Now, because this is the first such study, we don't really know much else, but by itself this is already pretty intriguing. Then we have mechanism number 2, the ionospheric effect. This is based on another Japanese study that was only recently published, and as always you can find in the description. And this model is based on what's referred to as a capacitive coupling. It's basically a term from circuit designs and from electrical engineering. And so in this case we can think of Earth, and specifically Earth's crust, as one of two ends of some kind of a leaky battery, with the other end being the ionosphere, or basically the upper atmosphere. It would roughly resemble something like this. And so in the study, scientists suggest that fractured zones in crust containing high temperature, high pressure water, very often in some kind of a supercritical state, may actually act as an electrical component or as a capacitor, which then starts to store electric energy. And when there's some kind of a really intense solar flare that hits planet Earth and specifically hits the ionosphere, it may increase the density of electrons inside the atmosphere, pushing them to lower altitudes, which then results in a kind of a coupling effect, with the negative charge in the sky inducing a strong electric field inside the crust below it, which then creates electrostatic pressure and, according to their calculation, results in pressure that can reach several megapascals. This is actually comparable to the stress caused by various tides and the effects from the moon. And this extra push might be just enough to cause already stressed fault to suddenly collapse, or basically to trigger a massive earthquake. And well, here they noted that the 2024 Noto Peninsula earthquake in Japan seemed to have happened right after a period of intense solar flare activity, which in their case fits the model. But as a side note, and I guess note of caution, as I previously mentioned, sometimes both earthquakes and solar flares do coincide. Nevertheless, assuming this idea has any merit, and if there's maybe any other evidence found in the future, this might also explain another intriguing phenomenon we've discussed a few years back, the phenomenon referred to as the earthquake lights. You can learn about this in one of the previous videos in the description, but this is basically a report of various lights happening during earthquakes that seem to have no other source of origin. And it's still not clear if this is just the result of a lot of exploding transformers on the surface, or if it's actually a phenomenon that could be actually the result of this electrostatic pressure from the upper atmosphere. So in this case, maybe this could be the visual manifestation of the idea explained in the study. Although a slightly different proposition from 2020 suggested that maybe this is some kind of a reverse piezoelectric effect, where high electrical potential between the atmosphere and the ground then generates electrical discharges, which turn into mechanical stress. And so here the study from 2020 identified a correlation between density of solar protons and the effects on the ionosphere, which were then linked to large earthquakes worldwide. And specifically, once again, this involved a bit of a delay. Here the peak seemed to happen approximately 1 day after the protons reached the atmosphere. And so, in other words, some of the studies suggest that there might be some kind of an electrical effect that causes so much pressure on the surface that it then results in some kind of a seismic activity. But at this point, all of this is still mostly hypothetical, and we're unfortunately not anywhere close to being able to predict any of this. And so we're not at the point where we can have some kind of an earthquake weather app that would allow us to predict where earthquakes might happen. But intriguingly, in one of the recent studies, researchers from UT Austin were able to leverage machine learning algorithms and to basically come up with the first version of an algorithm that successfully predicted 70% of earthquakes a week before they happened. Here this was based on 5 years of seismic records. And so here, by using data from China, the algorithm was able to predict 14 earthquakes within approximately 200 miles of their actual location, and with even almost exact magnitude. And here these forecasts were issued weekly, providing a 7-day advance warning, with the system only missing 1 earthquake, but unfortunately also issuing 8 warnings that were basically false positives. Now this was actually part of a competition that nowadays is kind of popular in China, and so here different AI algorithms try to compete in order to see who would predict this the best. And so out of 600 algorithms, this one algorithm seems to have been the best. But the problem in this case is of course that, well, this could have been completely by chance. And that's of course because this was based on a limited data, and there were 600 competitors, with basically just one of them essentially guessing the results a little bit better than anyone else. And so in some sense, we cannot say that AI can predict any of this, especially because there were so many false positives, and because some predictions were very far from the actual event. And so I guess a good start, but definitely not something we can use yet. And especially because in many cases, earthquake patterns vary significantly by every single region. And so here the geology of the region matters quite a lot. But the researchers behind this recent study are now planning to test the system in a lot of other seismic regions, such as California, Japan, and Texas. And so for all we know, they might come up with something in the next few years. But at least at this point, as of early 2026, earthquake prediction is still a kind of an impossible problem. I mean, in principle, it could be solvable, but as it stands, no one has solved it yet. Hello wonderful person, this is Anton, and it's now been basically 3 years since that famous eruption. The eruption of the Tonga volcano that happened on January 15th of 2022 that basically took everyone by surprise. The eruption that produced one of the most explosive events in modern history, and the eruption that had a lot of different effects on planet Earth. And as you can imagine, in the last 3 years, we've actually discovered quite a lot of things about this eruption, and some of these discoveries are somewhat surprising and even kind of mind-blowing. And though you can learn about some of the previous discoveries in a few videos in the description below, today we're going to discuss some of the recent stuff, including the most recent paper from just a few weeks ago. And so let's discuss this in a little bit more detail, starting with some of the most bizarre observations pretty much right after the eruption. So first of all, we know that this eruption generated the highest ever recorded volcanic plume that reached the altitude of 57 kilometers. Here's what it looked like from outer space, with this picture taken from the International Space Station. And right as this explosion was happening, something really bizarre was observed from outer space. Here, some of the satellites discovered that this also produced the highest number of lightning flashes we've ever seen. You can essentially see all of this in this video, with every single dot that you observe being a lightning flash. And here the measurement suggested approximately 2600 flashes every single minute, which is basically more than we've ever seen anywhere on the planet. Intriguingly, at some point, there was even a very bizarre ring of lightning, roughly around 7200 kilometers in radius, that formed around this volcano, which was an early indication of how extremely powerful this eruption was. And what's even more interesting is that it actually sent an enormous pressure waves around the atmosphere, which is of course what's visible in this particular animation, that produced so much energy that it actually forced the ionosphere to produce a very strange bubble of plasma that was enough to disrupt satellite communication around the planet. This was the result of what's known as EPB, or equatorial plasma bubble, that forms when a lot of different winds mixed with plasma and also electric fields start to move through the ionosphere. Here's roughly what these EPBs look like if observed from the outer space. And this was so extremely powerful that it even affected GPS communication around the planet by disrupting the GPS satellites. And that was of course just a few hours after the eruption, so these were basically instantaneous effects. But then obviously we had some other effects underwater. Now the most obvious one was the Megatsunami that formed almost right away, with the large tsunami waves even reaching South America, and some waves even reaching the Caribbean. But here, a much more surprising result was discovered on the ocean floor. Turns out this eruption blanketed the entire ocean around the volcano, covering everything with ash and decimating all local wildlife 100 kilometers away from the center, basically killing almost everything that lived underwater in the vicinity of the volcano. This was reported in several studies that managed to investigate the ocean floor following the eruption, and it looks like the damage here was absolutely extreme. Something that was actually not known prior to this, and something that was a little bit more destructive than what we observed on the surface. But then there was also one really important question in regards to the effects on the atmosphere. Did this actually affect the climate in any way in the last 3 years? And if so, how? Well, it turns out that several studies did come out in the last few years, basically trying to assess if any of the heat waves in the last few years were possibly the result of this. And looks like the answer is potentially no. So far, most studies seem to have discovered only a very minor contribution to the overall temperature increase of just 0.015 degrees Celsius. And that's possibly because this volcano was actually really unusual. It did not just release sulfur compounds, which are usually responsible for cooling down the planet. This was an underwater volcano, so it actually released enormous amount of water vapor, which entered the upper atmosphere and increased the overall levels by at least 10% for several years now. And though the temperature effects might have been quite minimal, turns out that there was an unusual effect from all of this. It might have affected the ozone hole. And so strangely enough, all of this water that entered the upper atmosphere possibly helped chemical reactions which do destroy ozone layer, and this is maybe why the ozone hole over Antarctica has been opening up slightly earlier every year since the original eruption. So basically here we had effects nobody suspected and nobody anticipated. But then there was a slightly different study that focused on something entirely different. The focus here was on life on the island when the island was just born and basically following the eruption. And that's because this island, Tonga Hapai, was really only created in 2015, the result of this ongoing volcanic eruption that actually has not stopped even now. And so since its original formation, for approximately 7 years, this island was continuously colonized by various types of life. And here scientists wanted to find out exactly what's happening and what kind of life. And the expectation was that, in terms of, for example, bacterial life, we would find something similar to what we usually find in glaciers, such as cyanobacteria, and basically bacteria that then help plants grow. And actually, if you look at these early pictures from 2021, you can actually already see a lot of plants on the island, suggesting that the entire island became colonized by various types of plants in just mere months. Although here this was extremely likely the result of birds, specifically bird droppings that very often contain seeds. But when these bacteria were analyzed prior to the 2022 eruption, they turned out to be completely different from what was expected, because a lot of bacterial life on this island was actually similar to what we usually find in hot springs and hydrothermal vents. It was metabolizing sulfur and various types of atmospheric gases, suggesting that all of this life actually did come from nearby hydrothermal vents and was slowly creeping up the island, colonizing the surface. And for microbiologists, especially the ones studying the origins of life, this is a really exciting discovery because it kind of potentially shows us how early life that very likely also developed in the oceans eventually colonized the life on the surface as a lot of these islands were born. And so basically this whole island was populated by different types of life that came from deep underground, not life that came from the surface or even from the ocean nearby. But as we know today, it only lasted for 7 years, with the island becoming this afterwards. So yeah, note to self, don't buy real estate on volcanic islands. But after years of research, scientists studying seismic waves coming from this eruption now discovered something else. Something we didn't really know about, and something that was not detected up until recently. Turns out, 15 minutes before this eruption, and before these extremely powerful waves, there was another wave that was not visible at first, but has now been found in the seismic data. And so here in this recent study, Takuro Horiuchi and his team used seismic data available from several locations around this island to uncover signs of what's known as a Rayleigh wave. A type of a wave often triggered by various volcanic eruptions, earthquakes, or a lot of other powerful events affecting planet Earth that moves along solid surface as a type of an acoustic wave, very often resembling an earthquake. Here this is a combination of a compression and a shearing movement that basically makes Earth move in the way you see right here. And the observations here suggest that this particular wave traveled for a very long distance with quite a lot of power, but actually started 15 minutes before the major eruption. In other words, this was a kind of a precursor, or even some kind of a warning signal, that was only really discovered now in this recent paper. But this unusual wave and this unusual signal didn't just warn us about this potential eruption, but also possibly explains what may have happened inside. Here, research suggests that this was a result of a relatively large crack above the volcano that started to basically vibrate, producing these Rayleigh waves right before a major collapse, when huge amounts of water rushed in, mixed with the superheated magma, and eventually led to this explosive event as all of this magma pressurized and eventually exploded. And that of course means that by detecting very similar events in the future, there might be a way to create a lot of different warning systems for a lot of different island chains that are often affected by nearby volcanoes or by similar explosive events. And so here we're talking about a lot of these locations along the so-called Ring of Fire that could potentially benefit from the results from this study. But I guess what's even more surprising here is that even after 3 years now, we keep discovering new things nobody knew about and uncover new phenomena this unusual volcano produced, mostly because of the advances in seismic detectors and because we understand these events so much better. Which of course means that we might actually come back and talk more about this in the next few months as new studies come out, new discoveries are made, and especially as we discover what this volcanic eruption did to our planet and what long-term effects it produced. Hello wonderful person, this is Anton, and today we're going to discuss some of the more recent discoveries in regards to a somewhat unusual anomaly right here on planet Earth. An anomaly related to the dynamic invisible shield around the planet known as the Magnetosphere. The magnetic field generated deep within the Earth that protects all of the life on the surface from the constant bombardment of the solar wind and dangerous cosmic radiation. But what you might not be aware of is that this particular shield is not uniform. It's either a little bit stronger or a little bit weaker in certain locations. But recently, using some of the most high-precision satellite data available to us, researchers confirmed that the most massive weak point on the planet, the point referred to as the South Atlantic Anomaly, seems to be not only growing, but is also undergoing significant complex changes, suggesting that there is something changing within the planet that we still don't really understand. And so let's discuss this idea in a little bit more detail and talk about what all of this means and how this might affect the planet. And by the way, all of this, as always, is based on this particular study by Finlay, Claus and Gillette that was published in late 2025. But in order to understand what the study is about and what this anomaly is about, let's briefly discuss the shield first. And here's a very good simple illustration showing us its main function around the planet. But how exactly is this generated? Well, based on a lot of studies from decades prior, researchers believe that all of this is generated by the liquid outer core that's primarily made out of iron and nickel. And so here this vast ocean of swirling molten iron, thousands of kilometers beneath the surface, creates electrical currents as it moves around and as it churns around through the process referred to as the geodynamo. And while in an ideal world, or in a lot of theoretical predictions, Earth's magnetic field would look almost exactly like a typical magnet, perfectly aligned with the axis of the planet and perfectly equal on every side. But in reality, it's not. The magnetic axis is tilted by at least 11 degrees from the spin axis and is constantly shifting around, and it even shifted dramatically in the last few decades. By the way, the video about this should be in the description. And the theoretical center of the magnetic field is not close to the Earth's geographic center, offset by hundreds of kilometers. And it's really this unusual offset that seems to produce some of these anomalies. And specifically this really large one we discussed back in 2020, SAA or South Atlantic Anomaly. In this region, above South America and the Atlantic Ocean, the magnetic field seems to be significantly weaker than anywhere else on Earth. Actually, in some places it's approximately half as weak as in certain locations on the planet. And though you don't really feel this on the surface, it does matter for anything in space. Since the field pushes away high-energy charged particles coming from the sun, in this location the shield has a hole, allowing the inner Van Allen radiation belt to descend to a much lower altitude of about 200 kilometers or 120 miles, which essentially starts affecting anything orbiting in this region. And so anything from crucial satellites in the orbit, or obviously astronauts passing through this, will usually be dramatically affected by the increase in radiation. And so any satellite crossing the SAA is usually exposed to much higher levels of ionizing radiation that bombards onboard computers and technological systems and sometimes causes data loss or even short circuits. This has actually damaged quite a lot of satellites in the past. And this is something that a lot of satellite operators always have to deal with. As a matter of fact, even the famous Hubble Space Telescope has to routinely shut down when passing through this region. But the most famous failure was in 2016. This involved a sudden unexpected failure of the Japan's Hitomi X-ray Observatory, a really expensive scientific mission that was launched a few years prior, that essentially failed in 2016, with the Japanese Space Agency eventually establishing that this was probably the result of the extremely high radiation above the South Atlantic Anomaly. And so after this, a lot of space agencies started to take this extremely seriously. So this is a very serious matter for space scientists and satellite engineers. But what exactly drives the weakness here? What produces this bizarre hole? Well, apart from the overall tilt and the offset of the magnetic axis, researchers believe it's linked to mysterious fluctuations near the outer core and the boundary within the mantle, with one interpretation suggesting that this anomaly is a consequence of some kind of a localized field with reverse polarity growing strongly in the region, which results in a much weaker magnetic intensity. In Earth scientists, this is usually referred to as the reverse flux patches. These are essentially areas where the magnetic field lines seem to loop back into the core instead of radiating outwards. But there is another potential source. Near this location underneath Africa, there is a massive chunk of dense rock located 3,000 kilometers below the surface. This is known as the African Large Low Shear Velocity Province. You can learn about this particular phenomenon in one of the videos in the description, but we know that there are two such chunks, and scientists think that it might be leftovers from an ancient impact with a planetary object, although there are other interpretations as well. Either way, this really dense mass seems to disturb the core flow, interfering with the generation of the magnetic field and leading to the observed weakening effect. But it's really because of the European Space Agency's missions that we now have so much more data and can actually make a lot more conclusions. And that's because back in 2013, ESA launched a very interesting swarm of satellites. They're known as the Swarm. Although technically it's not a swarm, it's just a trio, 3 satellites, but they're extremely good at producing very accurate data in regards to the magnetosphere. Here, these 3 satellites, Alpha, Bravo, and Charlie, provide extremely high-quality global magnetic field measurements that allowed us to track the evolution of the magnetic field between 2014 and 2025. With this picture basically showing us how everything changed in just the last 11 years. And so the most striking discovery in this case is a continued dramatic expansion of the anomaly and the physical change of the field that happened in relatively quick terms. And so here from 2014 to 2025, the region where the field strength is weakest, so below 26,000 nanotesla, seems to have expanded by 0.9% of Earth's surface area, or expanded by approximately half of continental Europe. This only took approximately 11 years. And on top of this, the minimum intensity for the anomaly continued to fall, decreasing by about 336 nanotesla in the same period of time. So on average it used to be 22,400, now it's just 22,000. But even more fascinating is the change of the shape of the anomaly. It seems to have expanded and developed a secondary minimum or secondary lobe stretching in the direction of Africa. And this seems to be linked to the development and movement of these reverse flux patches somewhere beneath the core mantle boundary. So essentially these changes seem to be happening inside the planet, but once again the exact change or the exact reason is still not entirely clear. But these reversed flux features under Southern Africa have actually been observed moving westwards, converging toward other reversed flux features that seem to move eastwards under the mid-Atlantic, with the expansion and change in shape suggesting that the South Atlantic anomaly may be in the process of splitting into two distinct cells. So, in other words, this might become two separate anomalies moving in two directions. And the growth of this anomaly continues a somewhat long-term trend that has even been seen by some of the earlier missions as far back as 55 years ago. So this is not something that's just developed, this is something that was going on for a long time. But the SAA or Southern Atlantic Anomaly is not the only area showing rapid changes. Here the swarm data also highlights significant evolution in the northern polar region. Here there are two main regions of strong field intensity, one over Canada and one over Siberia. And the changes in the relative strength of these two regions seem to be fundamental to the overall understanding of this core dynamo process that creates the entire magnetic field. But since 2014, the strong field region over Canada has diminished. And if you're Canadian, you're probably going to blame Trudeau for this as well. Now, I didn't vote for him, so I don't really care. And on top of this, the area of strong field above 57,000 nanotesla, which is actually one of the strongest on the planet, seems to have shrunk by about 0.65% or almost 1% on the Earth's surface area. Here, the maximum field strength decreased by 800 nanotesla. And so here the entire area of shrinking seems to be comparable to countries like India. So this was a relatively large change. But don't panic yet, it doesn't mean that the entire field is weakening, because Siberian field seems to have increased. The corresponding strong field region over Siberia grown by about 0.42%, increasing in maximum intensity by 260 nanotesla, and in area comparable to something like Greenland. And so this bizarre unequal change suggests that the decline in the Canadian maximum and the growth of the Siberian maximum seem to be directly linked. But I guess more importantly, seem to contribute to the movement of the northern axis, where the northern pole shifted towards Siberia a few years back. Once again, the video in the description talks about this a little bit more. And because these shifts are crucial for things like Arctic navigation, because they directly impact magnetic declination and magnetic pole position, trying to understand this is of course super important for modern shipping and for modern navigation systems. And so to understand all of this, scientists also look backwards, exploring historical anomalies through the technique known as archaeomagnetism, basically trying to analyze various magnetic particles trapped inside various ancient artifacts, such as for example clay vases or clay tablets, which were heated and then cooled down and normally trap the magnetic record of the planet inside of them. And so using this, scientists can normally recreate a kind of a snapshot of the magnetic field from specific times in history. And we know that something like this definitely happened at least several times in modern history. For example, during the Levantine Iron Age, there was something referred to as the Levantine Iron Age Anomaly, LIA for short. This was 3,000 years ago, and during this time the magnetic field over the Middle East seems to have also experienced an unprecedented intense spike in strength, that's still not entirely understood but was probably caused by something very similar. And so studying these anomalies and trying to connect them throughout history may one day help us understand how exactly all of this works, and actually help us predict them in the future, and possibly tell us a little bit more about when and how the complete magnetic pole reversal may occur as well. We just know that right now there are no signs of this potentially happening anytime soon, but if it does happen, it will definitely affect the technology on the planet. And we know quite a lot about magnetic reversals from the event that almost happened 41,000 years ago. Once again, check out the video in the description that talks in detail about this particular anomaly. But overall, these findings gathered over the last decade are absolutely crucial. Crucial not just for Earth sciences, but also because we now depend on this space technology so much. They definitely provide some insights into the underlying dynamics inside Earth, and suggest that a lot of these anomalies seem to stem from massive, large-scale movements of the molten iron deep within the core that sometimes interacts with certain chunks of stuff in certain regions on the planet. But there's obviously a bit of a constraint when it comes to data in this case, because right now we seem to only have a relatively short time span of observations, just covering a few decades. But in this case we're discussing something that obviously takes thousands of years to change and to shift around the planet. And that's why continuation of these high-quality missions is absolutely crucial, with the data from the Swarm mission being absolutely groundbreaking for helping us understand the changes in the magnetosphere. And that's why a lot of scientists today are currently advocating for extending this mission, and specifically the lifetime of the higher orbit satellite known as Swarm Bravo, because we need to have more data, otherwise we just don't really know where this is headed. And a longer mission will definitely ensure that we have high-quality geomagnetic observations, especially because we will have additional missions in the future, such as the ESA's NanoMagSat that's going to become operational in the next few years. But in this case, having continuous data without interruptions is very important. And in this case, once again, this is not just about curiosity or trying to figure out how things work inside the planet, because all of this now affects infrastructure we rely on every single day, and since we expect to launch thousands of satellites in the next few years, this will very likely affect many of them, costing millions and billions of dollars in loss if we don't really know what's happening. But when it comes to scientific curiosity, we actually still don't really understand what's up. We know it has something to do with the churning of iron inside the core, but how these anomalies are produced and how they evolve is definitely not something anyone can explain yet. Hello wonderful person, this is Anton, and today we're going to discuss some of the more unusual discoveries when it comes to planet Earth. But specifically discoveries in regards to Earth's gravity and a somewhat unusual gravitational anomaly that was just discovered by accident in one of the recent studies. And normally these gravitational anomalies reveal secrets hidden deep beneath the surface that traditional surface geology could never uncover. And so today we're going to discuss some of these recent discoveries and compare them to some of the similar discoveries from the moon, and of course discuss this most fundamental phenomenon or this force on the planet, gravity. But first, let's briefly discuss how we know all of this and how this is usually studied. Because a lot of these incredible discoveries could not be possible without specific satellite missions. And I think this one right here is probably the most important and the most famous of them all. This is a pair of NASA satellites referred to as GRACE, Gravity Recovery and Climate Experiment, that's been going on for at least 2 decades. And the point of this mission is pretty simple: mapping the entire planet and trying to identify various irregularities when it comes to various values for surface gravity. And so here the point is to try to discover the actual gravity value compared to what's expected or what's predicted based on a theoretically perfectly smooth Earth model. Because these gravitational anomalies do exist everywhere, and that's because none of the objects in the solar system, including our own planet, are perfectly spherical or uniform. And because gravity is directly proportional to mass, and also since different materials inside the planet will usually have different density, they're going to create slightly different gravitational pull, and they're going to produce slightly different values for gravity in every location on the planet. Now, the actual differences are very minuscule, but they're still there. And in order to measure all of this, scientists came up with this very brilliant mission. It essentially uses twin spacecraft orbiting extremely close to one another, and they orbit in such a way that they can actually see each other, projecting lasers as you can see in this picture. And so here, as the first satellite passes over a certain area, if it detects slightly stronger gravity, it's actually going to speed up momentarily, which will change the distance between satellites and will be visible because of these very precise laser observations. And really because of, well, lasers. They're just such an incredible tool for super precise measurements. And so here, by precisely measuring changing distances, researchers can then start mapping the gravity of every single point these satellites pass over, which is of course where you usually get something like this. Now this is extremely exaggerated, but this essentially shows you slight field anomalies measured in milligals. And for this to make sense, we have to understand what these milligals are. Milligal is essentially a measurement of gravitational change, with the Earth's standard gravity being approximately 980 gals, or 980,000 milligals. In case you're wondering, gal here stands for Galileo. And 1 gal represents 1 centimeter per second squared. And so you can see that some of the values are approximately 50 milligal, which is almost nothing compared to 980,000 that represents the average on the planet. But nevertheless, these values are quite specific and quite significant. And as you can see in certain regions on the planet, there are unusual anomalies, specifically positive anomalies and negative anomalies. Now, positive anomalies usually occur where the measured gravity is just a little bit stronger, and this normally indicates the presence of dense subsurface material, like for example some kind of a metallic ore, or maybe dense oceanic crust. And so here this can actually be used in detecting new mining materials, or in trying to map the invisible plate tectonics. So this is essentially useful for both mining industries and geologists. And the negative anomalies, which are obviously produced by slightly lower gravity, usually represent massive basins filled with light sedimentary rock, or potentially unusually thick continental crust. So this is what you see right there in Africa, which makes it a vital tool for planetary exploration, or technically even lunar exploration, because something very similar was also done on the moon. And so, for example, for mining, when scientists detect some kind of a negative anomaly, this can help delineate sedimentary basins, which very often hold oil and gas reserves, because these rocks are usually much less dense compared to surrounding basement rock. Whereas the positive anomalies can reveal extremely rich iron deposits or any other dense metal. But for geologists or scientists trying to understand the planet, this is also how we can study plate tectonics and even the structure underneath, such as the crust and the mantle. Because here gravity maps are perfect for revealing faults, folds, or structures inside the planet and discovering boundaries between Earth's crust and the denser mantle below. And so essentially this is one of the most important tools for geological sciences. But it's recently also become super important for studying climatic changes. Because here over the years, Greece became essential for what's known as time-variable gravity data. Essentially changes in gravity fields that seem to happen over months or years, and which seem to be the result of redistribution of water on the surface. And this includes tracking groundwater, melting glaciers, and changes in the sea level as well. So this is a crucial tool for hydrology and climate forecasting, which is what it's basically been used for the past few years. And so when you hear about any studies involving changes in water distribution, that's usually where this data comes from. And the data here is super accurate, because here even millimeter changes are usually observable and visible to these satellites. But this is where we come to today's mystery and this somewhat bizarre observation. Because for decades, scientists believed that a lot of these time-variable gravity signals would probably be coming from various surface processes, such as water, ice, or maybe atmospheric mass shifts. Which is of course what you can actually see in here, based on these previous maps made over the years. But this is where things get bizarre, because a recent analysis that came out just a few days ago uncovered some really bizarre data that didn't make sense. A very strange event that originated far deeper than anyone predicted, and seems to have happened between 2006 and 2008. So essentially this happened over a decade ago, but somehow was missed until now. And the peak for this event apparently happened in January of 2007. And this was an anomalous, large-scale gravity signal that seemed to have emerged over the eastern Atlantic Ocean. This is essentially what you see in these pictures. And interestingly enough, this was not a small event. It seems to have spanned approximately 7,000 kilometers or about 5,000 miles, which reflected a significant mass redistribution. And here researchers spent a lot of time comparing the observations against every known process, and it basically confused them for a very long time. For example, models shifting water, or any kind of atmospheric changes, just did not make any sense. This signal could not be explained by either water or atmosphere, because it was just too powerful, and the amount of water required to produce this would be just unrealistic. And this forced the scientists to come up with a different hypothesis and a different explanation. Here they had to go down thousands of kilometers below the surface, down to what's known as D layer, a layer located near the boundary between the mantle and the outer liquid core. And here, at a depth of 3,000 kilometers, they possibly discovered the source. And here the evidence points at something that's not expected at all. An extremely rapid density change deep within the Earth's solid interior, and very likely resulting from some kind of a mineral phase transition that happened in just 2 years. Or basically, there was some kind of a chunk of stuff that then transitioned from one phase to the other, kind of like water changing into ice, which basically changed its density, and that affected the gravity. And this study is so detailed that they even identified what most likely changed. The material in question is the mineral referred to as brigmanite, also sometimes referred to as a silicate perovskite. And it just so happens that under extreme pressures and under extreme temperatures, which we obviously do find inside the planet, this mineral can change its crystalline structure from perovskite to post-perovskite, which sort of resembles this. And this change usually involves a dramatic density increase, which can obviously affect gravitational measurements. And since in this case the temperature generally determines the depth where this occurs, here it was most likely triggered by some kind of a vertical motion, for example material rising from the base of the mantle, which possibly caused the transformation, with all of this happening extremely fast. So once again, kind of imagine ice melting and becoming water, just because it went from somewhere much colder to somewhere much warmer. But interestingly, the movement of this material was extremely close to another geological mystery, African Large Low Shear Velocity Province, LLSVP. The bizarre structures inside the planet that we discussed in some of the previous videos in the description, whose origin is still not certain, but that obviously influenced the planet in certain ways. And so here this change caused a rapid mass redistribution, very likely affecting the African LLSVP and making it shift a little bit. And what's even more interesting is that apparently this event also coincided with something else, a somewhat unrelated anomaly in the Earth's magnetic field. So here this event spatially and temporarily coincided with the geomagnetic jerk, or basically a sudden rapid change in the variation of the magnetic field, which seems to have happened around the same time. And so this connection suggests that these deep mantle mass redistributions may directly influence the fluid core motion that generates the magnetic field as well. And though it's not entirely clear how all this connects yet, these incredible new discoveries will most likely lead to some really important explanations about what happens inside planet Earth. But right now, researchers believe that this phase change very likely caused the topography inside the planet to change just enough to shift things by about 12 centimeters every 2 years, which is what was observed in 2007 and why we saw so many anomalies during this year. And these discoveries are also important because they essentially offer us a unique window into the rapid dynamics inside our own planet, proving that the solid mantle, even at its base, can undergo some relatively fast structural shifts that only take a few months at most. And shifts that can even impact observations in gravitational fields and even affect the magnetic field as well. But here, just for funsies, let's maybe also take a look at our partner, the Moon, because for many decades the Moon has also been studied quite thoroughly and has also been mapped by very similar missions. And that's because, unlike Earth, the Moon is relatively solid and relatively stable, and so here various anomalies usually tell us a little bit more about the ancient events that shaped this object. And for decades, scientists noticed something really strange. A lot of spacecraft orbiting the Moon, especially over large impact craters, would routinely veer off course. And so having a permanent and stable orbit around the Moon has always been extremely difficult. And so it turns out that compared to planet Earth, the Moon's gravity field is incredibly bumpy. Which becomes pretty obvious when you look at this map, or when you compare the anomalies to our own planet. Here, a lot of the gravitational anomalies are usually 6 to even 10 times more powerful. And so today a lot of these mass concentrations are referred to as mascons, with the mysteries surrounding their formation once again largely resolved by similar twin missions, in this case referred to as GRAIL. The satellites that kinda look like this. GRAIL stands for Gravity Recovery and Interior Laboratory. And so this GRAIL data show that a lot of these mascons don't just create strong centers of gravity, they often appear with a very unusual bullseye pattern. A center of strong positive gravity surrounded by alternating rings of weaker and stronger gravities. And the reason why the Moon seems to have this is its violent past. So basically a lot of these large asteroid impacts that the Moon experienced over the years seems to have produced most of these bizarre anomalies. But turns out that these bullseye patterns only formed under specific conditions, when the asteroid struck much thinner crust, and specifically because this allows the denser material from the underlying mantle to then rise toward the surface, concentrating mass near the surface and creating these bizarre mass cones. But the areas of the moon with much thicker crust resisted these formations, with impacts not resulting in any of these mass cones or these bullseyes. And so by comparing the gravity anomalies on Earth and the moon, it really shows us how fundamentally different a lot of planets and moons seem to be. And so on the moon, the gravity anomalies are primarily fossilized geological records. A lot of them are billions of years old and have not changed much for a long time. And they essentially reflect ancient cataclysmic impacts that left permanent mass concentrations trapped beneath the surface. Actually, most of them occurred during the late heavy bombardment over 3 billion years ago. But on Earth, gravity anomalies are both static and dynamic and allow us to study so much more. For example, these static anomalies help us map stable geological structures like mineral deposits or even understand plate tectonics, whereas the dynamic parts help us understand the changes in the water and atmospheric pressures, or even learn about these bizarre structures underneath the planet. And so these are definitely super important studies, and even help us challenge the traditional view about the deep mantle and the locations near the core. Even though we always thought these were extremely slow processes, this study based on the observations from 2007 tells us otherwise. And so this is not just academic, this is about building a comprehensive model of planetary behavior, and about understanding somewhat surprising and still poorly understood workings of planet Earth. And as always, you can learn about all of this in a study by Charlotte Anton and the team you see on the screen. Hello wonderful person, this is Anton, and today we're going to discuss some of the recent and somewhat mysterious discoveries coming from right here, our planet Earth. The discoveries in regards to something inside the planet that once again is somewhat difficult to explain and currently makes no sense. And in this case involves the discovery of somewhat unusual, never before seen, hidden structures that seem to be in a lot of different locations on the planet underneath the crust, but whose origin is currently impossible to explain. And so let's discuss this in a little bit more detail, but also let's start with the obvious. In the last decade or so, because of the advances in seismic detectors and also the overall increase in computing power, it actually became relatively easy for a lot of different geologists to extremely accurately study the internal structure of our own planet. And that's because we have a lot of different seismic receivers on the planet, all capable of detecting even minor earthquakes. And here, these earthquakes and the waves they produce basically serve as a kind of ultrasound. They allow us to see inside the planet and allow us to uncover a lot of hidden structures by basically detecting how fast or how slow certain waves move in certain locations. So basically all these seismographs that constantly detect and record earthquakes allow us to calculate internal structure of the planet by calculating the speed of each wave, which then determines what's inside. And that's because the speed of these waves depends on what kind of a wave it is and the overall density of material they pass through. Or to be more specific, the density and the elasticity, which is essentially how the scientists eventually discovered the presence of these huge structures we refer to as LLSVPs, or large low shear velocity provinces, that we've discussed previously in a lot of different videos, because even today it's not entirely clear what actually produced these enormous structures, but they either represent ancient continents or potentially leftovers from the ancient planet that collided with planet Earth. But on top of this, in some of the recent videos, we also discussed the discovery of an additional core inside the planet, the so-called innermost core, and a lot of other bizarre features, such as huge chunks of seafloor, discovered in just the last few months. So basically, in just the last few years, there's been a lot of different discoveries. You can learn about some of them in some of the videos in the description. But here the principle was always the same. By listening to these waves from various locations, it becomes possible to find areas where the rock, for example, seems to be colder or potentially has different composition. So basically, in certain locations, the earthquake waves seem to act a little bit differently. And so based on these unusual anomalies, geophysicists can usually find unusual structures, or even reveal certain composition inside the mantle, or in some cases even inside the core, allowing us to understand and study our own planet without physically going there, drilling into it, and trying to collect samples, which by the way, even today would practically be impossible. Even today, one of the deepest holes is only like 12 kilometers in depth. And so when it comes to research involving geophysics, and specifically research involving plate tectonics, or basically the movement of continents and their interaction over time, surprisingly, a lot of previous theories so far have basically been proven correct by studying geological deposits underneath the crust within the mantle by using these ultrasound techniques. And so, for example, researchers here expected to find a lot of different sunken continental plates very close to various subduction zones, where we know one of the plates sinks under the other, eventually forming some kind of a deposit inside the mantle. And so quite a lot of these tectonic plates that have sunk over time have actually been discovered very close to subduction zones as predicted, which did confirm a lot of theories of plate tectonics and helped us understand how all of this works. As a matter of fact, most of our geological understanding and the understanding of how the planet evolved in the last 4.5 billion years is kind of based on many of these assumptions that have basically been proven correct so far. But turns out that this plate tectonic cycle might still have some secrets. And these secrets have now officially been revealed based on even more complex simulations and even more complex analysis that managed to use the data from all of these seismic receivers combined with the analysis by a supercomputer, specifically this one, PIS-DAINT, located in the Swiss Alps, that allowed the scientists behind the recent study in the description, so Thomas Schutten and his team, to essentially create the highest resolution model we've ever had of all possible anomalies on the entire planet, going as deep as 1,000 kilometers. And though this model once again confirmed the presence of these plates close to various subduction zones, it also discovered something entirely different. Here it discovered very similar formations that actually resemble submerged plates, or possibly some other really dense structures formed by something else entirely, in locations where nobody expected them. In most cases under very large oceanic or continental plates, where there are basically no subduction zones, or no other zones that should be able to produce something similar. As a matter of fact, in most of these locations, there is no evidence of any kind of subduction activity, no presence of previous plates, and no explanation for how something like this could have formed. Right now, these are just anomalies. And the only reason it was just discovered in the early 2025 is because of this newly created model known as the procedure full waveform inversion that required all of the seismic detectors in order to produce this observation. And naturally, because it was so computationally expensive, here they also needed a supercomputer. But the question right now is, what exactly are these? What are these lost worlds that seem to be located in many places, with the biggest ones being in the Pacific Ocean and under South America? And well, for geologists, right now this is a really big mystery because there's really no model that would explain any of this, and current plate tectonic theories suggest that these should not exist and there should actually be nothing there. Which basically means that there is something we still don't understand about the internal dynamics inside planet Earth, and it looks like our planet is able to produce these huge, massive structures using some kind of a technique we still don't understand. Or what this means for the evolution of planet Earth, and how this affects the planet over time. Although funnily enough, one of the researchers basically tried to explain this in layman terms by using a common comparison with a typical ultrasound you might get from a doctor. Here he basically compares this to a doctor examining blood circulation with ultrasound, discovering a lot of different arteries, but then finding one where he really doesn't expect in someone's buttocks. I mean, it was a pretty funny analogy, and it does actually reflect what was discovered in this study, so I thought why not include it in this video. So yeah, basically, these discoveries are kind of like finding an artery inside someone's butt. But right now the explanations are sort of missing. I mean, there are some, but none of them are concrete. For example, one explanation here is that this is not just material from the last millions of years, but could actually be extremely ancient material, very likely rich in silica and a lot of heavier elements, that's been there since the formation of the mantle approximately 4 billion years ago. So in some sense, maybe this is just leftovers from ancient Earth that has not changed much over time. And that's despite the convection inside the mantle that should have destroyed it a long time ago. Alternative explanation here involves something different. Maybe this is iron-rich rocks that possibly accumulate as a result of mantle movement, in this case forming unusual focus points, where the mantle motion basically brings everything in a certain region on the planet, where it then accumulates over time. But the reality is that all of these are just assumptions for now, and there is really no explanation. As a matter of fact, this is just another new mystery from inside the planet that once again highlights how little we know about the planet and how much we still have to learn. I mean, for all we know, maybe these are actually just tiny layers that were shed from the crust itself, that for some reason remain in the mantle and were never recycled. Hello wonderful person, this is Anton, and today we're going to discuss something somewhat intriguing that was recently discovered in one of the oceans right here on planet Earth. A previously unknown massive crater caused by an impact millions of years ago that was massive enough to cause an enormous tsunami, and the effects from which are still observable even today. And because I've always had a very strange fascination with a lot of these impact craters, maybe it's because I was always fascinated with dinosaurs and their extinction was caused by one of these objects. Because of this, I was always super curious about other potential collisions and especially the effects they might have produced on planet Earth. And so in this video we're going to discuss some of these new discoveries and exactly what this means, and discuss everything we know about this newly discovered crater. But first, I guess, let's start with the obvious. Based on the size of our planet, and based on what we see on the surface of the moon, technically our planet is supposed to be covered in craters all over the place. And at some point it may have been, but because of powerful erosion forces, plate tectonics and a lot of geological activity, pretty much most of these ancient craters eventually got erased. And only some of them are still visible today, whose existence is mostly known because the impacts occurred somewhere on the continental plate, where erasing them would be a little bit more difficult. But because most of the surface of planet Earth is actually water, it would be even more difficult to find signs of craters in the ocean, mostly because over millions of years they would leave only a few clues behind. But nevertheless, in the past few decades, some of these ancient craters hidden in the oceans have actually been discovered, with at least one of them that we've discussed not so long ago, potentially associated with a major climatic shift. For example, right here off the coast of Africa, roughly around 400 kilometers west of Guinea in the Atlantic Ocean, there is something that seems to be 9 kilometers across and something that formed 66 million years ago. And surprisingly around a very similar time frame as the other impact that killed the dinosaurs, with the impact located in Mexico. And this is known as the Nadir crater. It seemed to have been formed by a much smaller asteroid, possibly 500 meters across, and it's currently located 300 to 800 meters below the seabed. And so along with the Chicxulub crater, which is obviously much larger at 180 kilometers, here we have evidence for at least 2 major impacts in a very similar time frame, and for all we know possibly formed from some kind of a larger parent body. Then we have the evidence for what's known as the Eltanin impact. You can learn more about this in one of the videos in the description, but in essence here in the Pacific Ocean, we seem to have a lot of evidence for some kind of a major impact based on a lot of iridium anomalies and signs of some kind of an ancient tsunami that affected the coast nearby. But because there is no crater, there is actually very little we know about it, although it just so happens that when this impact occurred, around the same time Earth was also experiencing a lot of cooling. And right now a lot of different theories propose that this impact potentially kickstarted the ice ages on planet Earth, because it happened around the same time as the first formation of the ice caps in the northern hemisphere. And here this rock was estimated to be about 1 to maybe even 4 kilometers in diameter, but because it hit the ocean where the depth was at least 4 kilometers, it essentially produced no crater, evaporating completely after hitting the surface. But except for these confirmed craters, there are approximately 20 to 30 smaller craters that have been proposed in various studies, but have not really been officially confirmed yet. And so when it comes to confirmed ocean impacts, we really just have like 3 essentially. And that's I guess until now, because now we seem to have 4. Based on this new study by Wisdian, Nicholson and the team you see on the screen, we now have a confirmation about one of these incredibly rare hidden underwater craters, with this one located beneath the North Sea. And it's now referred to as the Silver Pit crater. Although in this case, this has been actually a hypothesis for at least several decades. So basically here it was assumed to be a crater, but we finally have enough evidence to suggest that this is indeed a crater and not something else. And so where exactly is this? Well, it's actually not so far from the United Kingdom. Roughly around 130 kilometers or 80 miles off the coast of Yorkshire. And though originally discovered back in 2002, this is actually when the geologists were looking for oil and gas and were exploring the North Sea for potential sources, this unusual circular feature actually did have several explanations. And it was obviously very difficult to determine exactly what this is, because it was covered by 700 meters of sediment. But it was pretty large, 3 kilometers or 2 miles across. And so for over 2 decades, scientists were divided about what produced this. Mostly because trying to prove these structures is kind of challenging. And so, for example, one of the more mundane explanations involves some kind of a geological salt, or maybe even volcanism, which was technically the preferred explanation by the Geological Society back in 2009. But this debate was finally settled in 2025 thanks to new high-resolution 3-dimensional seismic images, and of course the analysis of rock samples as well. And so here's how we know that this is an impact crater and not something involving volcanism or moving salt. First of all, this contains a lot of shock minerals. Here, by finding shock lamellae, or microscopic pressure deformations within minerals like quartz and feldspar, researchers had their first hint that this involved something ridiculously powerful. And that's because to produce this, you need to have an atomic rearrangement of the crystalline structure that can only happen in extreme pressures around 10 to 13 gigapascal, which we usually expect from something super powerful like a hypervelocity impact. On Earth, volcanism or salt movement cannot generate these. Then we had the morphology based on 3-dimensional imaging. Here, by using seismic data, researchers identified features consistent with complex impact crater structures, including a central uplift beneath the crater floor and various concentric faults. And there were also secondary craters with individual circular depressions up to 150 meters wide that were surrounding the main object. This is usually formed when the initial impact creates a kind of a splashback, with additional rocks then falling back to Earth away from the central impact. And normally on Earth, these features are rarely preserved, mostly due to erosion. And so here the evidence was indeed pretty strong. But based on its depth and based on the analysis of sediment, we can now determine when it potentially happened. And this seemed to have happened during the Middle Eocene epoch, roughly around 43 to maybe 46 million years ago, with the impactor very likely being at least 160 meters across, so much smaller than some of the previously discussed impactors, but definitely still large enough to cause a lot of damage. And when it struck the shallow sea, it very likely generated a tsunami at least 100 meters high. This was based on computer simulations that tried to recreate this impact. And based on the recreation, it actually suggests that this impactor very likely struck the planet at a low angle trajectory coming from the west-northwest, very likely creating a massive explosion and a lot of debris headed in the same direction. But there's obviously this one important question that we need to answer. Did this impact do something to the planet, kind of like the Chicxulub impact 66 million years ago, or the more recent Eltanin crater that potentially triggered the ice ages? This was during the Eocene optimum, and based on what we know about the climate changes during this time, it's as if there was nothing happening at all, which actually does confirm some of the previous propositions in regards to why dinosaurs went extinct and why the ice ages started to begin with. During both periods, the Earth was already kind of shifting here and there, and it just needed that final trigger to initiate a complete change of climate. Yet during the Eocene optimum, because there were no major shifts, it's quite unlikely that this impact did anything except for causing massive destruction in the North Sea in the immediate area around the impact. And so, as of 2025, Silver Pit Crater officially joins this somewhat exclusive list. But because we're still learning about what effects these impacts even have on the planet, it's a little bit early to tell or to make any conclusions about any potential influences on our planet. But what we do know for sure is that the Silver Pit Crater now joins a very exclusive list. We only have like 190 terrestrial impact craters in total, and only 4 have now been officially confirmed to be underwater. And so with the Nadira crater in Africa, the Chicxulub in Mexico, and the signs from the Eltanin impact southwest of South America, we basically now have 4 official impacts that happen somewhere in the ocean. And so since impact craters are so rare on our planet, this is a pretty big discovery. And on top of this, it's also very well preserved. Here, ocean sedimentation happened very quickly, so a lot of these preserved structures under the seabed will eventually help us understand how craters form, while also helping us understand how the interaction with water influences everything as well. And so by studying the results from these past impacts, we can eventually predict what could happen if there was another collision in the future, especially because rocks of very similar sizes technically represent some of the least known and some of the most dangerous objects in the entire solar system. Of all the asteroids out there, objects of very similar size of about 100 to 500 meters basically represent some of the biggest hazards today. But you can learn more about this concept in one of the previous videos in the description. But I guess, what's next? Well, we still have approximately 30 unconfirmed underwater craters, and so by using this study and based on the discoveries from here, we can now apply the same results and figure out if those other structures are also impact craters, or possibly something else entirely. And so based on recent success stories from the Silver Pit and the Nadir craters, both of which have been confirmed relatively recently, we can now use very similar techniques in a search for these Earth's hidden cosmic scars left by ancient impacts millions of years ago. But in this case, this is also a success story for scientific research, because after decades and decades of a lot of back and forth, and also a lot of debates and a lot of propositions, we can now definitively say that this was indeed an impact crater caused by an asteroid and not a volcano, with all of the evidence from this particular study basically being enough to prove everything. But I guess now it will be interesting to find out if someone can actually discover something in regards to various changes during this period, in order to find out if there was maybe any effect on the planet at all. Hello wonderful person, this is Anton, and today we're going to be discussing some really intriguing discoveries about ancient Earth. And specifically, we're going to be stepping back into the deep past, approximately 500 million years ago, when life on Earth was arguably at its most bizarre. We're going to be discussing what's known as the Ediacaran period, a transformative era approximately 635 to 541 million years ago, that eventually resulted in some of the most major transformations when it comes to the evolution of life and the formation of all complex life known to us. But specifically, we're going to be discussing some of the recent studies and the potential causes for all of this that may actually have a very bizarre and somewhat unusual geological origins. But I guess first, so what exactly was this era like? And what was Earth like back then? Well, here pretty much most of the life was still in the oceans. At this point, the ground itself was most likely barren, but the oceans were not bustling with fish and crustaceans, and instead was covered in life forms that barely resemble anything alive today. So all sorts of squashy fans, tubes, donuts, and flat discs, with many of them actually resembling plants, but still being creatures and animals, like for example, an enormous animal that grew up to about 4.6 feet long, or about 1.5 meters, potentially representing one of the largest specimens from this period, with some other organisms that we've discussed previously representing all sorts of creatures entirely different from anything today. For example, the unusual tiny slug-like creature Kimberella, that may have resembled something like this, was essentially one of the first complex animals that could potentially move across the seafloor and very likely graze on the seafloor. And for Earth, this was a huge achievement, because for the most part prior to this, all life was single-cellular or extremely primitive. And so here we had this bizarre explosion of complex multicellular life that today is referred to as the Ediacaran biota, a monumental leap in evolution. But the question here was always, why? Why now? Why not before? I mean, Earth had like billions of years to try this sometimes in the past, but for some reason it only happened approximately 600 million years ago. So what drove this bizarre sudden blossoming? And turns out the answer may lie several thousand kilometers below our feet, the liquid iron core. And so let's discuss the Earth's magnetic field, which as we know today is very likely formed by the churning motion of the molten iron in the outer core, and it's absolutely essential for making our planet habitable. And so the magnetosphere shields the atmosphere from dangerous solar radiation, solar winds, and cosmic rays. And if we hadn't had this early field on Earth, the solar winds would most likely strip pretty much everything from the surface, starting with most of the atmosphere and eventually water. But the thing is, based on a lot of geological evidence, we know that something really bizarre happened approximately 591 million years ago. Here the shield failed dramatically. Or to be more exact, it seems to have almost failed, and this particular period of extremely weakened magnetic field potentially lasted for several million years. And so quite a lot of new research that studied magnetism locked in ancient crystals revealed several major details about this time. Now in this case, a lot of these crystals are sort of like geological time capsules. They preserve the magnetic field record and even tell us how intense the field was during certain times. And that's because when these crystals form, they tend to solidify in a certain way depending on the strength of the field. And so here scientists discovered that for a period of about 26 million years, the Earth's magnetic field was profoundly weak. And while earlier evidence from the province of Quebec suggested that approximately 565 million years ago, the field was about 10 times weaker than today. We've actually briefly discussed this in some of the older videos. But in a lot of recent studies, something else was discovered. The latest geological evidence gathered from 591 million years ago, and specifically from ancient rocks in southern Brazil, discovered that the field was actually much weaker, up to 30 times weaker than today, or at least 3 times weaker than previously assumed. And this ultrafield intensity is the weakest known magnetic field in Earth's history. But there is something really interesting that happened around this time as well, because the failure of this Earth's essential protection system may have actually triggered the emergence of advanced life. But first, let's briefly discuss why we think this field almost failed. Now once again, the geodynamo is powered by the motion of molten iron in the outer core. And this is something that's been going on Earth for billions of years. And turns out that this process was getting more and more inefficient. And that's because Earth was actually cooling down, and as a result, the core inside was moving less and less. But unlike today, something else was very different about Earth back then. The innermost part of the core was actually entirely liquid. It seemed to have lacked the solid core. And so approximately 600 million years ago, by the Ediacaran period, at this point the entire system was basically running on its last legs. And so during this time the field started to fail. It was growing weaker and weaker, and even started showing signs of potential collapse. But fortunately for life on Earth, something changed deep inside the planet. And the answer to this enduring geological mystery seems to be directly tied to the formation of the solid core. Because as the planet cooled down, a lot of this molten iron started to transition from one phase to the other. And so around this time, researchers believed that the inner core began to crystallize, a process referred to as nucleation. And the moment this started happening, it surprisingly provided a really important energy boost. This transformation pushed the mechanism from the weak, unstable state into a very strong, stable magnetic field that we have today, because in this case, the solid inner core suddenly provided an important surface for the convection to become more efficient, and also added a lot of extra heat, which was suddenly released from inside. And so we now had this new sudden source for this continuous generation of geodynamo inside the planet. And so the recovery of the field strength seems to be directly associated with the growth of the inner core. And this was very likely also crucial for the prevention of the drying out of our water-rich, ocean-rich planet. But in this case, it was really timing. Timing was everything. The magnetic field was at its weakest right when the first complex life started to diversify. And as the field bounced back during the subsequent Cambrian period, this actually provided life with this new important magnetic field that now served as the shield for the next 600 million years. Although here we have this new crucial hypothesis: a weak magnetic shield helped complex life evolve. And we do have some evidence about this as well, and it seems to be all related to oxygen. And so, for example, for some of the larger animals during this time, like those in the oceans during the Ediacaran period, in order to become successful, and even in order to evolve, they did require a lot more oxygen. And traditionally, scientists thought that maybe this was provided by various cyanobacteria, or various photosynthetic organisms living in the oceans that would steadily produce oxygen over time. But in this case, the weak magnetic field offers us an alternative and also complementary explanation. And that's because the weaker magnetosphere provides less shielding from the solar wind, which actually allows a lot of lighter gases, especially hydrogen, to be lost to the atmosphere. We've actually seen this many times happening around Mars, even today. And when hydrogen is lost, more oxygen may remain in the atmosphere, instead of reacting with hydrogen to form water vapor. And so in this case, the ultra-weak magnetic field over those tens of millions of years very likely caused a sustained loss of hydrogen, which would then lead to increased oxygenation of the atmosphere and even the surface ocean. And so here the influx of oxygen might have been the key factor that suddenly allowed all of this somewhat complex life to start reaching new thresholds. And most importantly, it enabled more complex life to evolve, with even more complex bodies that would usually require a lot more oxygen. And so in this case, the weak field may have allowed oxygenation to cross a kind of a threshold, aiding animal evolution for millions of years. And so it's really around this time that we suddenly see sudden explosion of various types of animal life that today we often refer to as the Cambrian explosion. And so most of these bizarre animals that formed millions of years after were possibly the result of this extreme oxygenation following the Ediacaran anomaly. But the Ediacaran magnetic anomaly is not just about the weakness of the magnetic field, it's also about instability, because for years the geological record presented us with a major puzzle. Here a lot of paleomagnetic data seemed very chaotic, showing a lot of wild and conflicting variations in the magnetic field of the planet, which led some scientists to assume that maybe something really bizarre was happening inside the core, the mantle, and the crust, and maybe the entire magnetic field was wandering all over the place. But this recent study from 2025 provides us with some really precise and very detailed work that potentially explains this as well. And so here, by running a detailed analysis of volcanic rocks from certain regions in Morocco, they were able to precisely constrain the timing of these magnetic shifts. And what they found seems to confirm this true chaotic activity. In this case, the magnetic shifts seem to have happened in just thousands of years, as opposed to hundreds of thousands like in modern times. And more importantly, this did not involve any kind of a pole shift, but seemed to just involve extremely chaotic magnetic field during the entire period, with the field increasing and decreasing in strength extremely rapidly. And this might be the only such period in Earth's history, at least according to the data and all of the evidence. And this also provides a lot of support for the hypothesis that the chaotic field preceded the solidification of the inner core. In other words, this potentially happened right before the solid core appeared and right before that crystallization period. With this study once again confirming that the magnetic anomaly seems to be directly linked to the crystallization of inner core, seems to have resulted in an extremely chaotic period, but most importantly, was directly correlated to the major evolutionary step in Earth's history. The evolution of a lot of bizarre complex life during the Ediacaran and the Cambrian periods, and the sudden appearance of complex animals in the ancient oceans. And so without that recovery, scientists believe that Earth might have looked extremely different today, perhaps somewhat similar to Mars, or perhaps even similar to Venus. And even though these strange Ediacaran creatures eventually vanished during the Cambrian period, and even these Cambrian creatures eventually disappeared too, their brief existence, fueled by this extreme chaotic period on the planet, suggests that some of these major crises in the Earth's history, and especially planetary crises involving geology, can sometimes unlock biological potential on the entire planet and eventually result in super complex life. Which means that understanding a lot of these deep Earth processes is crucial for interpreting the planetary past, and also important for understanding how life may form somewhere else. So basically, just looking for planets in the habitable zone is not enough. We have to also consider the geological history of the planet, because in this case, the unsung hero of the story seems to be the Earth's core, and specifically the dramatic shifts at just the right time. But at least that's based on some of the recent studies that, as always, you can find in the description. We'll definitely come back and discuss this more once there are some additional discoveries. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon, where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. Alternatively, you can also buy the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.